Okay, we're recording. So we're talking about electromagnetic induction, which basically breaks down into two different laws. Okay, the first one is Faraday's law. Let's go ahead and write it down. We've already seen this in lab last week. Faraday's law is determined experimentally, so it's something that you're playing around with current in wires and magnetic fields and things, and you're noticing that if you change the magnetic fields or you change the currents, then you're generating other currents and other magnetic fields called induced magnetic fields or induced currents or induced voltages. Okay, so Faraday's law, stated mathematically, has to do with this induced EMF here, E, which is caused by a change in magnetic flux. Okay, and so let me remind you what magnetic flux is. It's exactly the same as electric flux, but with a magnetic field instead. So magnetic flux is this integral, and it's a surface integral of the magnetic field on some piece of a surface described by this area vector dA. So we can draw a little picture to go along with that, to kind of complete the idea here. So here's kind of my surface. It looks a little something like this. And we always draw magnetic fields green, right? So suppose we have some magnetic field lines coming through this surface. And our area vector here, let's say at this point right here, is kind of coming out like this. Right, and then these two are making an angle, let's call it theta, with respect to each other, because we do have this dot product right here. Remember, we always have this dot product when we talk about flux. Okay, so a nice simple thing to remember is if you have like a uniform magnetic field, uniform case, so you have a uniform magnetic field and you just have a rectangular area, then this kind of complicated integration simply becomes B times A. And then maybe if there's an angle between that rectangular area and the magnetic field, then you'd have like a cosine theta here. Okay, so since the field is uniform, you could just integrate this thing right away after taking the dot product, and you get B times A, and maybe a cosine theta in there. So just kind of exactly like electric flux. Just a couple notes here about the magnetic flux. One thing that we don't want to do for magnetic flux is we don't want to do our integration over a closed surface, because this is always equal to zero. Remember, that's one of Maxwell's equations. Okay? Your book calls this Gauss's law for magnetic fields. This equation is not typically called Gauss's law for magnetic fields. This is actually the no-name equation. What was I saying? Gauss's law for magnetic fields. Let's go ahead and put B field here. Right. And just speaking of Maxwell's laws, or Maxwell's equations, Faraday's law is the last one that we haven't seen yet, right? So we've seen Gauss's law, we've seen this no-name equation, we've seen Ampere's law, and now we're talking about Faraday's law. And then later in this chapter, we'll actually make a correction to Ampere's law so that it's true in general. We'll talk more about that later. Okay, so this is the idea here. So if we have a time-changing magnetic flux, then we get an induced voltage, an induced electromotive force. Okay, so let's go ahead and write that. So time-changing magnetic flux. And I didn't finish writing this, so induced voltage. Okay, so that's the idea. So today we're going to focus on calculating with this, and maybe we'll get some practice with our right-hand rule as well. Are there any questions up to this point? If there are no questions, you can just give a thumbs up, and I can just keep going here. Okay. So the next thing we'll do is we'll just get right into some examples. So I have some examples right here ready. Okay, so for this example here, we have a nice figure that I just pulled from the book. Let me give you a bit of a problem statement to go with it. Okay, so we just want to find the induced EMF and the induced current. Let's go ahead and I could just write that by hand. So we're looking for the induced EMF, which we're going to get from Faraday's law, and we're looking for the induced current, which we're going to get, if you take a look at the problem over here, tells us we have some resistance here in the circuit, right? And so probably going to get the induced current from Ohm's law. Okay, and then for the second part, part B here, we are going to find what effect would replacing this loop with an insulator have on the induced EMF and induced current. Okay, so replacing that conducting wire there with an insulating material instead of a conductor. So what effect would that have on the EMF and the induced current? Okay, so do we want to work on this one together, or do you guys just want to work on this one by yourselves? So give me a thumbs up if you want to work on this one by yourselves, or if you want to see me go through the first one. Okay, so we only have one person here wanting to work by themselves. Okay, so I'll go ahead and, or maybe two people want to do it. Oh no, okay, Andrea says together. All right, so let's go ahead and, I'll go ahead and set this one up here. So part A, find the induced EMF and induced current. Well, we're talking about Faraday's law here, so that's kind of the first thing I would go to. So I'll write down Faraday's law first. Okay, so there's Faraday's law. Let's go ahead and put the M here. I see in the problem statement here, I'm given a lot of stuff that I kind of need to figure out how to work into this expression here. So this part right here, dB dt, and this area right here. Okay, but I know magnetic flux is something like magnetic field times area. So I can write down the flux We'll start with the most general case, but I think we can see it's going to simplify because we have just like a fixed area there. It's just a circle there, right, or a disk, and the magnetic field is all pointing in the same direction, but it's increasing a little bit. So there's going to be a delta B associated with that, but there's not going to be any cosine of the angle or anything like that. So it's kind of a simple integral here. So we'll integrate B dot dA. Okay, but let's take a look here at our loop. Let me draw a simpler kind of loop down here like this. So this is our loop here. And in this loop, we have the magnetic field going vertical like this. And of course, the area vector for this loop is also going to be pointing vertical in the same direction as the magnetic field. So when we do the dot product here, no cosine of any angle there. The two are parallel, right? So cosine is going to be 1. So we can write this as integral B dA. And the area element here is just given by this disk that I'm highlighting here in blue. The area of that disk is simply 2 pi times the radius, or excuse me, pi r squared, right, for that disk. But that's actually just given to us as 120 centimeters squared up here. So we don't need to calculate like a pi r squared for that. We can just take this value here. The magnetic field, now this is maybe a little bit of the tricky part of this argument. Now the magnetic field here is changing with respect to time, but it's not changing with respect to the location in this area. So the magnetic field over here on the left is the same as the magnetic field over here on the right, and it's the same as the magnetic field over here in the kind of the front and in the back. The magnetic field on that disk is constant. Okay, so that's maybe a little bit of a tricky point there. Even though the magnetic field is changing with respect to time, we're integrating over the area here. And so the magnetic field can be pulled outside of the integral. Does that make sense? Give me a thumbs up if that made sense. So the magnetic field is constant with respect to the area, even though it's changing with time. Okay, it's a couple thumbs up. Let me know if I need to repeat that again. So magnetic field changing with time, but not changing with area, so we can pull it out. Okay, so let's pull it out. So it's B times the integral of dA. And this integral right here is simply A. It's going to be the 120 centimeters squared, but we don't need to plug numbers in just yet. Right, we want to get to an answer first. Want to get to an equation that has all the terms in it, and then plug in the numbers, right? Okay, so we have B times A for our magnetic flux. So this was a nice simple case that I kind of mentioned before. Now we need to calculate d phi dt. So d phi dt, because that's what we need for Faraday's law here. So if I want to calculate d phi dt, then I'm taking the derivative with respect to time of the magnetic field, right? But I want to, or excuse me, the magnetic flux. So I want to plug in the magnetic flux here as B times A. And I have a question for you guys. So is the area changing here? Is the area of that loop changing? You can answer in the chat if you want. Let's see if we can get a couple people here. Couple no's. Anybody think yes, that the area is changing? Anybody unsure? Okay, it looks like everybody's saying no, so that's a good sign. So yeah, that's correct. So the area is not changing here, so no need to do a product rule here. The only thing that's changing is the magnetic field. Okay, the only thing that's changing is the magnetic field, and so we have simply the area times dB dt. So just kind of pulling the area outside of the derivative there because it's not changing with respect to time. Okay. So the only thing that matters here for the that's generating the induced voltage here is the time changing magnetic field. And I think we saw in lab that you can also change the area. I think one of the cases was to play around with the size of the wire loops. I can't remember exactly, but you can also have some cases, we'll see in a little bit, you can have some cases where you kind of maybe have a wire and you kind of stretch it out, and that can change the magnetic flux as well. You can have a uniform magnetic field, but you change the area and you induce a voltage or a current. All right, so we're pretty much ready to plug in numbers at this point. Yeah, Sean. So number one, we're not worried about that just yet. So we'll work that in there in a second. Okay, so we're ready to plug things in here. So I just want to look at the magnitude for a second and forget about the minus sign. And we'll talk about the minus sign after we get an answer here. So for the induced voltage, what we have is simply A times dB dt. Just plugging in what we got here. Let's highlight it in red. Plugging in what we got here in for this right here. Okay. So we can just plug in numbers at this point. So what is A? A is 120 centimeters squared, but maybe we want to convert that into meters so that we stay in MKS units, right? So 120 centimeters squared, multiply this by 100 centimeters in 1 meter, right? But we have centimeters squared here, so we better like square this thing. Okay, and then that's our conversion there, times dB dt, which is given to us over here. So this one right here. So 0.020 Tesla per second. And ultimately what this is going to work out to, Tesla meter per second is a volt for units. Okay, so let me go ahead and you guys do the same. So get your calculators out, go ahead and calculate this, and I'll go ahead and use my calculator over here on the computer. So we want to plug in 120 divided by 100 squared. Make sure you got your parentheses in the right spot, right? We don't want to make a calculator error. And then times 0.02. Okay, so I get 2.4 times 10 to the minus 4 volts. Okay, yeah, so Duke and Sean getting the same thing there. Give you guys some time here to catch up on the calculation. So let me know when you guys are good. You can give a thumbs up. Or maybe you calculated something different. Let us know. Okay, so I think I think that's pretty much everybody. Okay, so now the question, and maybe I leave this for you guys to kind of, you tell me what to do. How am I going to get this induced current now? So you tell me what to do in the chat. How do I get this induced current? Okay, I'm seeing some answers here. That's a good sign. So Ohm's law, right? So we're going to take this induced voltage, we're going to divide by the resistance in the circuit, right? So we're going to divide by the resistance in the circuit. That's Ohm's law. Delta V over R equals I. So let's write it out. So the current I is equal to delta V over R. So Ohm's law here. And in our case, we have this induced EMF, right? So I'll change it to that E there. Let's go ahead and plug in the numbers. We don't really have to do much more than that at this point. And the resistance is given to us as 5 ohms. Volt over an ohm is going to give us an amp. And so this is going to be about 5 times 10 to the minus 5. Yeah, so 48 microamps. That's pretty good there. Pretty close, I mean. Okay, so questions about that one? I think that one's pretty straightforward. Give me a thumbs up if we're good to now talk about part B. Okay. So we'll talk about part B, and then we're going to come back to this minus sign here, okay? So I haven't forgotten about this minus sign. That minus sign is Lenz's law, right? So let's talk about part B. So what effect would replacing this loop with an insulator have on the induced EMF and induced current? Well, first of all, if we replace the wire, and this is a question for you guys, so you can answer in the chat again. If we replace the wire with an insulator, does that change how the magnetic field is changing? So is an insulator going to change how the magnetic field is changing? We have 3 no's in the chat, and I'd like to see some more people kind of give their input. Okay, so I think the general consensus is no. I tend to agree with you because the magnetic field is due to the kind of the magnets outside, right? Doesn't have anything to do with the insulator. How about the area of that loop there? Is that area going to change if we replace the wire with an insulator? Is the area of that loop going to change if we replace the wire with an insulator? So I have 1 no here. Of course, when we replace the wire here with an insulator, we're not going to change the parameters of the problem, right? We're going to keep the shape the same. The area is not going to change. What is going to change? Well, if we have an insulator, then insulators don't allow the motion of charge, right? The resistance is going to change. Right, Sean. So the resistance is going to change. This value of R is going to be huge compared to what it was before. So if the resistance changes, then I suspect that that's going to have something to do with Ohm's law, right? The resistance changes. So what's going to be affected here? Is the current going to be affected? If we make R really big, doesn't that make the current really small? What about the voltage? I see that the voltage goes into Ohm's law as well. So would I be correct in saying that the induced voltage would also change? David says no. Why doesn't the induced voltage change? Maybe you can explain your answer, David. Feel free to chime in with your own answer while David is typing out his. So why doesn't the induced voltage change? Resistance increases, causing the current to go to zero. Yes, but I'm asking about the induced voltage now. So why doesn't the induced voltage change? So how did we find the induced voltage here? Did we find the induced voltage using Ohm's law here? Sean says, we haven't changed the area, angle, or rate of change of the field. Right, so we got the induced voltage over here from Faraday's law, not from Ohm's law, right? So we want to use Faraday's law to determine whether the induced voltage changes. And so the area, magnetic field, rate of change, the angles haven't changed. So those are things that go into Faraday's law. So if d phi m dt hasn't changed, then the induced voltage will not change. So just to complete this question here, we could say for part B that E doesn't change. And we could say that I decreases, perhaps to zero, right? Because if we put an insulator there, it's going to be really hard to have a current, right? But you could still have a current in an insulator. It's not impossible. Okay, so that completes that question. So give me a thumbs up if we're good on that, if that makes sense there. Any questions? Okay. We'll go ahead and go to the next example now, and then this time I'll have you guys work on it. Okay, so here, is anybody still maybe writing? I'll leave this up for a second and just show the next figure here so I can get the problem statement here. So for this next question, it's kind of like one of these generator style problems. So what you're seeing in that figure is kind of a simple current loop in a magnetic field, which is kind of the basic principle of a generator, right? So let's take a look here. So we have a 500 loop circular wire. And let's just, circular wire coil. Radius of 4 centimeters. Placed between 2 magnets. With a uniform magnetic field. Field makes an angle 60 degrees with the plane of the coil. B decreases at a rate of 0.200 Tesla per second. What are the magnitude and direction of the induced EMF. And now that I'm actually writing this question out, I remember that I did forget about the minus sign in the last problem. So let's go ahead and scroll back up for a second. I'll give you time to write that down in a second, okay? So what is the direction of the induced EMF here? So they've given us a label. They've given us a label here. If you look at the figure, there's an A and there's a B. And we should be able to determine which of those leads is the positive and which is the negative for the induced voltage, right? So we have to use right-hand rule for that. So I would invite you to get your right hands out. If you're looking at the camera, this is my right hand right here. Remember, sometimes it's mirrored, right? So that's up to you maybe to like mirror the image or something. So this is my right hand. I see that the magnetic field is increasing in the vertical direction. So normally, if I had magnetic field in the vertical direction, that would be due to some current given by the wrapping of my fingers. So if my fingers are wrapping around in this direction, maybe I could just full screen for a second just so you guys can see just a little bit better. I'll stop the share so you guys can see me full screen. So this is my right hand again. So if my thumb is in the direction of the magnetic field, usually in a loop of wire with current, the magnetic field being vertical means the current is wrapping around like this, according to my right hand. So the current is going this way. But Faraday's law has a minus sign in it. So if the field is increasing in this direction, then my induced current isn't going to be this way. It's going to oppose the change. It's going to be in the opposite way. Okay. So it looks like by the right-hand rule, increasing B means you increase the current this way. But no, Faraday's law has a minus sign. And so we change the direction, the opposite direction. Okay, so let me get maybe like a color that stands out here. Pink, and the current is going to be flowing in this direction, the induced current. And actually it is already labeled on this problem here. So this is the induced current, and that is due to the minus sign here in Faraday's law, this minus sign right here. Okay. So if the current is flowing in that direction, then that means since the current is flowing in this direction, then we have a what is it called? Induced EMF in this direction here. So, by the way, this wire is a conductor with resistance. So you have to be careful about how you label potential difference across a conductor, right? So in this instance, we're not being told that this is a wire with zero resistance. If this was a wire with zero resistance, then we would kind of treat this like a kind of like a battery, and current would flow from high to low potential. But in this case, the wire is given as a resistor with resistance 5 ohms. So for resistors, you have to remember that the side the current flows across first is the positive side. So let me get a blue here. So this side right here, oh, excuse me, oops. This side right here is the positive side, and this side right here is the negative side. Okay. So maybe that's a little bit, that's all the way back from our chapter on DC circuits. So when you have a resistive element, the current comes into the positive and leaves on the negative. Okay, so as I've drawn it here. Okay. Questions about that? That's kind of important to make sure that we can get the direction, and we're going to get maybe some more practice with that in the next section, Lenz's law, when we get through a couple of these examples. But any questions about that now? Okay. let's go ahead and go to the next example. All right, next example here, like I said, is a little generator style problem here. So we have a loop, and we're going to take a look at how the induced voltage is in the loop. So we have a situation here where we have many loops inside of a coil of wire, and we have the radius of those loops, and we've placed it between two magnets with a uniform magnetic field, and the field makes an angle 60 degrees with the plane of the coil, so as labeled here in the diagram. And B decreases at a rate of 0.2 Tesla per second. What are the magnitude and direction of the induced EMF? So the first thing that I would want to make sure that everybody understands here for this problem is that this is a loop of wire here. So this is a side view, right? So this thing really is like a loop. So, maybe looking something like this with the magnetic field kind of going in like this, right? So it is a loop. Remember, crosses means going into the sheet, right? So this is like a loop here. I'm trying to draw this a little bit three-dimensionally here. And so let's try to maybe, so this is like the area vector there, three-dimensionally, and then maybe the magnetic field is going like this here. So this is our angle of 60 degrees here. Excuse me, that's the 30-degree angle. Okay, so that's the first thing you gotta understand. So it's a loop of wire, and there are many loops. And so this is a three-dimensional picture here, not a two-dimensional picture that we're seeing here. So when they ask us, what's the magnitude and direction of the induced EMF? It may be that let's say the negative side of the induced EMF is going to be like into the screen, and the positive side is going to be out of the screen, right? So we have to be careful about that. We have to understand how to label that direction properly. Okay, let's go ahead and do groups for this one, and I'll come around and help you get started if you need a little bit of explanation on this one. But there's one more point I want to point out. This is, again, a Faraday's law problem. It's a Faraday's law problem, so we're looking at something like this here. But in this particular problem, and what is actually characteristic of a lot of these problems, is you have multiple loops in the circuit. Whenever you have multiple loops, you have to imagine you take a ring and there's a change in flux for that ring. So there's a change in flux for this ring. But if I put a second ring on top of it with the same dimensions, I have 2 times that amount of change. If I put a third ring on top of that, I have 3 times. So if I put 500 loops on top of each other, I have 500 times the magnetic flux change. Okay, so you simply multiply by the number of turns. You don't have to have an N in this formula. You can just remember that the magnetic flux is going to be 500 times that amount because there are 500 turns. But in a lot of books and in class, I'll just write the N in there explicitly just to remind you. Okay. All right, that's all I have to say. So let's go ahead and break into some groups now, and I'll come around and help you get started if you need some help. And then I guess let's do it like this. Okay, we'll do 3 per room, okay? And then Bridget, maybe we could talk. Do you want me to like drag you into the rooms with me, or?
I'm fine just staying out. Thank you.
Okay. Okay, yeah, so everybody go ahead and join your rooms then. Okay, so you just stay here. I'm gonna go to each of. Basically, what I do is I just go to each of the rooms and just cycle through them.
Okay, perfect. You're doing a great job with teaching, so I'm really happy. Good job.
Thanks.
Sorry you gotta have this is your second dose now?
Yeah, I got it on Monday, like right before
Oh
my
no.
class. Yeah.
Good. Hopefully you feel better soon.
Yeah, actually, it's been better for the second one for some reason. The first one was killing me. This one is not killing me. So
Okay, good. Hopefully by tomorrow you'll be perfect.
yeah. Okay, I'm gonna get going now.
Okay, great.
Okay. Any questions here? Need some help, like getting started, or kind of understand?
I think I got it. I think I'm fine.
John is good. Phoebe, how about you? Hillary?
I'm okay, Professor, but I just have a quick question. Did you get my email yet? I emailed you earlier, like last night, so I wasn't sure if you got it or not.
Probably not. Then I can let me go ahead and check it right now.
Okay.
And Hillary, are you good on this one, or?
I'm a little confused still on why phi is 30 degrees.
Oh, yeah. Maybe I didn't notice that myself. That's probably bad notation. That's like the angle, not the magnetic flux. Is that the confusion, or why is that a 30-degree angle, or?
Uh, yeah, I think I was just confused on like, because when you use the equation, I'm assuming you're going to plug in the 30 degrees, right?
Um, yeah. Yeah, looking at it now, yeah, the area vector in the magnetic field is 30 degrees. That's right.
Yeah, so I was just wondering, like, why is it not 60?
So you have to remember, let me go ahead and share the screen. I just realized I'm not sharing. So there we go. So you have to remember that the dot product is between the magnetic field and the area vector, right?
Yeah.
So it's a dot product like this, and this is just the definition. This tells us how much of the magnetic field kind of penetrates that area element.
Mm-hmm.
And so the area vector is always normal to the surface. You remember that from Gauss's law?
Yeah.
It's always normal to the surface. So normal means perpendicular. So right here we have a 90-degree angle between the actual rectangle, which is the loop, and the area vector for that loop. So
Right.
when it tells you that like the plane of the loop is making a 60-degree angle right here. So the field makes an angle 60 degrees with the plane of the coil. So the plane of the coil is like where the actual like loops are, like
Okay,
that
I see.
disc. So that's 60. So then what's left is the 30, right?
Yeah.
So maybe it's worded strangely, but yeah.
Okay, that makes sense. Yeah, I was wondering where the 30 came from. That's why.
hmm
Mm-hmm.
Okay. Any other questions here, Phoebe? Oh yeah, your email. That's right. Let's see. Oh yeah. Uh-huh. I can do that for you.
Okay, yeah, thank you. I didn't get a chance to finish it, that's why.
Let me just do it right now. Where's it at? Tutorials. Do you need concepts too, or no?
No, I finished concepts. I just need the tutorials.
Okay. Till tonight or
Yeah, I can
Wednesday?
finish it tonight.
Okay. 11:59 tonight. All right, so I'll go to the next group then, yeah?
Yeah, thank you, Professor.
Huh? Let's go next one. Hello. I see we're working in chat here. Okay. Any questions for me? Your group ended up with Bridget, so that's why you guys have only two. Any questions here? Jaime, Sean? Okay, well, I'm just gonna let you guys work then. I don't even know what's going on here. Hello, how are we doing over here?
Still working on it.
Any questions, or we're good?
I'm good.
I'm good too.
Okay, we'll go to the next one. Oh, good. I'm here. Any questions? Andrea, Andrew, David?
So we're gonna take out the flux like you did from the previous problem, right?
Say
To
that
figure
one more.
that out. We're gonna take out the flux and figure that out separately and then plug it back in afterwards. Okay.
Yeah, exactly. Do the flux first and then like take its derivative. Yeah.
Okay, so since there's an angle, is it gonna be that's part of the B, right?
Let me share a screen here. That's part of this guy right here, the dot product.
Okay.
So you can see that the area vector and the magnetic field, let me see, where's my mouse at? Right here. So the area vector, which is here. Oh, sorry, that's the magnetic field. The area vector is this one. Those two are making an angle of 30 degrees with respect to one another, right?
Mm-hmm.
So in the problem statement, it says, the field makes an angle 60 degrees with the plane of the coil. So that means, you know, it's kind of strangely worded for like actually plugging numbers in from the question, but you kind of have to figure out, oh, it's not going to be 60, it's going to be 30. Because the area vector is going to be normal, or in other words, perpendicular to the plane.
Okay.
Any other questions?
No.
I have
Andrew?
a question.
Okay.
How would you determine the direction of the EMF?
So I do it using right hand rule, and then I just always make sure at the end, you know, I have to oppose that change, right? So in this case, it says B decreases. That means the flux is going to decrease, right?
Right.
So if the flux decreases, then that means that the change is pointing. Well, okay, so this is what I was about to say is slightly different than what I did in the previous example, but hopefully we're comfortable enough with the right hand rule we can figure this out. So the field is pointing to the right, right? If it decreases a little bit, it's still pointing to the right. Okay, so my right hand rule is telling me there should be kind of like a current with my thumb pointing to the right. There should be a current kind of coming out at the top and going in at the bottom of the loop. But I have to remember that it was a decrease in magnetic field. So since it was a decrease in magnetic field, I want the current to be kind of boosted in that direction to compensate for the loss of magnetic field. Did that make sense, or did I kind of word that strangely?
What do you mean boosted?
So what I mean is that the induced current will be in the same direction as the current that might already be there.
Oh, so it would just, you wouldn't.
Let me explain it again, because I don't think I did. Let me just explain it again, because I don't think I did a good job on that. So if there's a decrease in magnetic field, another way of thinking about it is that there's a vector dB, or delta B.
Okay.
And delta B is pointing to the left. So this is what B was. And so delta B is this bit right here. So in order to oppose that change, I should have an induced current which goes against delta B.
So would you use the right-hand method for the delta B vector?
No. That's where it gets tricky. So you have to use the right-hand rule to oppose delta B
Okay.
because of the minus sign. So since B decreases, that means you should generate an induced current which compensates for the loss of B. In other words, you need to have an induced current which gives you an induced B in this direction.
Okay.
It's a little bit tricky, but I think with a lot of right-hand rule practice, like you catch on really quick because it's not a lot of like calculation or anything. It's really it's like a thing you're using your hand to figure it out. So delta B in this case is a decrease. Since delta B is decreasing the magnetic field that's there already, that means your induced current will try to generate a magnetic field to compensate for the loss. In other words, it's opposing the change, right? That's what we said for Lenz's law and Faraday's law, that the induced magnetic field, the induced current, the induced EMF, they always oppose the change. That's basically a statement of Lenz's law. So the change is to the left, so the induced field should be to the right. And you can use the right-hand rule on the induced field and you'll get the right answer. You don't have to change anything. So if we do the right-hand rule on this induced field, what we get is we see that it's coming like this. So it's coming out at the top and it's going in at the bottom.
Okay. So you just kind of match it with like what you drew, like the dotted vector,
Yeah, so on this diagram here, I would
kind of.
let me back this up so it doesn't get too cluttered and I can go over the question later. There we go. So I could put a dot over here. It's coming out there and it's going in over there.
Right.
So it really requires it requires a few practice runs to figure this to really master this, but it's all you can do them kind of quickly because it's just using your right hand, right? You don't really have to write numbers and do calculations or anything to kind of figure this stuff out. So the best thing to do is probably go and look at the figures in the book. The book has some nice figures, and you can really practice with the figures there where the answer is, and then maybe you can draw some loops on the board and put some currents in the loops and say, okay, if B is increasing, what's going to happen, right? That kind of thing to really like master it.
Right. Okay.
Are there any other questions about this problem here? Andrew, I haven't really heard from you.
No.
No, okay, I'll go to the next group. I think actually I have to go back to group 1 now. Yeah. Okay, coming through for the second time, and then probably when I'm done with this, I'll close the rooms after like a minute. What's our progress here?
I finished, yeah. I put
Okay.
an answer.
Hillary, BB,
Yeah, I'm good too.
you're done?
Yep.
Yeah, same here.
Okay, why don't you just go ahead and go to back to the regular room then? I'll try and get everyone else out of here. You guys are done, which I suspect you probably are. Go ahead and just go back to the regular room. Any questions? It's decreasing, so the induced field is in the direction of B, yes. So the induced field is to the right. I'll let you guys keep discussing that. I'm going to close the rooms roughly 2 minutes, okay? Just so you know. Hey, do we have any questions here? Or we got it?
We got it.
Got it. Henry, you too?
Yep.
Okay, go ahead and just join the normal room. I know I'm back kind of quickly. Are we, what's our progress here? Andrea?
I'm still working on it.
Okay. I want to close the room soon because a lot of the other groups are done already. But I'm going to give you guys maybe like another minute to kind of work, okay?
Okay.
Hopefully you can get it done by then. And I will go over the questions, so. I was talking and muted. Okay, so I closed the room, so I'm giving the last kind of group a minute or so to finish up what they're working on, and I'll go over the question. Okay, I think everybody's here now. So let's go and go over the question. So I kind of wrote a little bit of stuff here while talking to you guys. So let's go ahead and start right here at the magnetic flux, which is kind of a good starting point for this question. So the first thing we want to do is calculate that magnetic flux there. And magnetic flux here in this case, we have constant area. Again, the loop is not changing its area. The magnetic field is decreasing. So only the magnetic field change is going to contribute to the change in flux over time. Okay. But here for the flux itself, we can go ahead and calculate kind of in a similar light that we did for the last example. So it's going to be B dA times cosine of the angle. And unfortunately, somebody pointed out to me that the angle is labeled phi. Okay, well, we'll draw this one slanted to the side, and we'll draw this one vertical or something to distinguish them. And again, the magnetic field is changing with time, but it is not changing with respect to the integration variable, which is the area. That's you get that information from the word uniform up here in the problem statement. So it's a uniform magnetic field. So we can pull B out. When we do that, we integrate dA. The cosine phi doesn't change, so it just stays there. Or we could also pull it out if we want to. So let's do that. So B cos phi, and then integral dA. Okay, this is just an area of a circular loop, right? So it's pi r squared in this case, and they give us the radius as 4 centimeters. So B cos phi, and then times pi, and then r squared here. And we can just plug everything in at the end, so I'll just leave it as pi r squared. So that's our magnetic flux, but we don't care about the flux itself, we care about the rate of change of the flux, right? In this case, So we want to take a time derivative, and in this case, only the magnetic field is changing. So let's highlight the magnetic field in red also. So the derivative is only going to act on the magnetic field. Everything else is constant. So the cosine phi is constant, and this area piece is constant. So when we take d phi by dt, we get cosine phi, the angle, times pi r squared put some extra parentheses there just to kind of distinguish those guys, and then dB dt, like that. And dB dt was given to us. In fact, it's even given to us as a negative value here as well, since it says B decreases. But what I usually like to do is just kind of always work with the magnitude of E, the induced voltage, and then just figure out the direction using like a Lenz's law or right-hand rule approach. Okay, so now we can take this information and write down E is going to be N, and I'm taking the magnitude, so I'm not writing the minus sign here, N times, and we just kind of write all this stuff in here. So dB dt, and then we have the pi r squared, and we have the cosine of that 30-degree angle. And now, I mean, this is a formula we're ready to plug stuff into, so that's what I'm going to do. So if you haven't already, go ahead and plug stuff in with me. And maybe I can write it out over here. So there are 500 turns. The rate of change of the magnetic field was given to us as 0.200 Tesla per second. And again, I'm taking the magnitude here, so I'm not writing the minus sign there, but it is a decrease. So normally a decrease comes with a minus sign. Maybe I should be a little bit careful. Maybe we'll put the magnitude symbol here just to make it a little bit more explicit. And that's the rate of change of the magnetic field. We have the pi r squared, so pi times 4 centimeters is 0.04 meters. Square that. And then cosine of 30 degrees here. It's got to be that 30-degree angle because if we look right here, this is the magnetic, well, I usually do green for magnetic field, so let's do green. So this is the magnetic field here, and this is the area vector here. So the angle between them was that phi. So I know it was 60 degrees was given in the problem. Maybe that was a little bit confusing, but I think most of you guys got it. So it's that 30 degrees that's important there. And now I'm ready to kind of punch this into the calculator. So go ahead and follow along with me if you weren't able to calculate it before. So 500 times 0.200 times pi times 0.04 squared times cosine of 30 degrees. Okay, and I come out with 0.435. Or maybe we can just round this up, volts. And I see some chats here. Yeah, so yeah, that's what I got too. So 0.44 volts. Okay, and Bridget has left us now. So she says, heading out, great job today. I hope you feel better and have an amazing birthday. So I don't know if I told you guys, but tomorrow's my birthday on Wednesday. But yeah. Okay, so how are we feeling on this example here? I'm getting one thumbs up. I think a lot of you got this one, so hopefully that means, okay. Yeah, so much more. All right, good. All right, so there was a point of confusion. I don't know if it was a point of confusion, but maybe a little bit of confusion, and that's like how to find the direction of the induced voltage here. I got asked this a couple times. So the trick is that it always opposes the change. So if I think about what's happening with the magnetic field here, I'll use green since I'm usually using green here. So if that's the magnetic field, and this was the magnetic field, so this is like B initial, and this is like B final, then there's a delta B, right? And delta B is final minus initial. Right? What would the direction of delta B be? Well, it was over here. It was this bigger magnetic field before, and now it's a smaller magnetic field. It was initial, now it's final. So that is a delta that points in this direction here. So that is the direction of delta B. Okay? That is the direction of delta B. Faraday's law says that the induced voltage will oppose the change. So if I know the direction of delta B, then I know the direction of the induced magnetic field. When I turn my magnetic field down, which is what I'm doing in this problem, Faraday's law says, wait a second, you're changing the system. I don't like that. Depending on how fast you change the system, I will fight you. I will induce a field in the opposite direction to oppose that change. So let's maybe use black here for the induced field. Depending on how fast that change occurs, I could have a big induced magnetic field. It could be this big, it could be bigger than the final magnetic field. There's nothing preventing that from happening. If it's a very rapid change, then that can happen. But the catch is, if it's a rapid change, that induced field isn't going to be there for that long. So this is my induced magnetic field. Notice it's pointing opposite to the change. It's pointing in the opposite direction of delta B. Okay? So it is this magnetic field that I can then use the right-hand rule for. So I can use the right-hand rule for this induced field. Use right-hand rule for B induced. To find I induced or E induced. Okay? That's what you want to do. You find the change and then you do something with the opposite of the change. So it's a little bit of a, like a 2 or 3 step thing here. Figure out what the change is and then go opposite to the change and then use your right-hand rule, right? So I guess it's 3 steps there. Find the change, go opposite the change, and then use the right-hand rule, okay? Maybe we can write that out. It's like a 3-step process here. So let's maybe move this side. We'll move this to the side. Just move this all the way over. This over. Move this little vector sign. Whoops. Now we have some space here, so okay. All right, just enough space here to make it work. So give myself a little box here. So step one. Step one, find delta. Okay, step two, go against delta. And then step three, right-hand rule. Okay, and now this delta doesn't necessarily have to be B. This could be I. This could be E. This could be electric field. It could be induced it could be a voltage. It could be an electric field. It could be a current. It could be a magnetic field. Whatever it is, find the delta. In this particular example, it was B, so let's fill it in. So then we want to go against delta B. And that is for B induced. Right? And then we use the right-hand rule for B induced. Okay, so you find delta B, then you go against delta B for B induced, and then you use the right-hand rule for B induced. Okay. So let's do it. Let's use the right-hand rule for B induced. We know the direction now. The direction is to the right. So for me, this is right. Let me stop the share for a second. So for me, this is my right. So my thumb is pointing to the right. Maybe I can look more at the camera. There we go. So this is to the right for me. So my right-hand rule tells me that the induced current would be coming out of the board, right? So the induced current is coming out of the board. Okay. Induced current coming out of the board. Oh, excuse me. I should be very specific here, actually. At the top. It's coming out at the top, right? Because my fingers are at the top. If I wrap my fingers around a little bit more, then you can see my fingers. It's coming, it's going in at the bottom. So out at the top, in at the bottom. Out at the top, in at the bottom. Hopefully, you're using your right hand right now to figure out that direction yourself. I already have it labeled, maybe some of you noticed. I already have it labeled over here on the figure. So it's a dot at the top, and it is a cross at the bottom there. So it's a dot at the top, and it is a cross at the bottom. Okay. Questions about that one? I believe that fully answers the question now, right? Oh no, sorry. We've figured out the direction of the induced current, but we haven't figured out the direction of the induced EMF. We need the direction of the induced EMF. Well, if the current is coming out at the top and it's going in at the bottom, then depending on you know, are we taking an ideal coil here with no resistance, or are we saying this coil has resistance? Typically with a coil, you treat coils as zero resistance. So the current is going to flow just like it would kind of for a battery. So it's, you know, from low to high. So in this case, we would have EMF, induced EMF, positive down here and negative over here. Of course, that EMF is continuous all around the coil. Okay, it's continuous all around the coil. And let me just check. Let me just check that for you guys here, just to make sure. If we go and check it in the book, that it's not saying something different here. And yes, that is correct. And actually, this is a nice. Yeah, I guess that's a nice way of thinking of it too. So the they say here in the book, and this is actually a nice little thing. So let me maybe stop sharing for a second and just kind of full screen myself. I kind of like this explanation they have at the end of this example in the book. So they say that once you find the direction of the induced field, which is this way, then your fingers curl in the direction of the positive EMF. So as I curl my fingers around, I'm headed towards the higher potential, the higher EMF. So you can use the right hand rule also to get the EMF. So whenever we use it to find the induced current, then we also know the positive direction of the EMF. Now I would be careful though, because like I said, whenever you have a resistor, current flows kind of in the opposite of that direction. So just be careful about that. You have to remember your Ohm's law. You may have an induced EMF like in a circuit or something. Just be careful about that sign. Okay? But what the book is saying for this particular example, in a coil, and again, I'm pretty sure the book treats all coils as ideal, meaning zero resistance. And that makes sense because when you analyze circuits with coils of wire, you can always put a resistor in series with the coil, right? I can always draw a circuit diagram where I have a resistor in series with a coil of wire, otherwise known as an inductor. We did that with capacitors, right? So we argued that capacitors, there's got to be some resistance there because a capacitor is made of like conducting plates, right? So we insert a resistor and then we analyze RC circuits. Same thing is going to happen with coils of wire. At some point, we're going to have to address that issue of there is resistance there. So what happens when we include the resistance? And that would be called an RL circuit, where the L stands for inductor. But we'll get to that later. That's not, I don't even think that's covered in this chapter, as a matter of fact. That's in the next chapter. By the way, before I forget, I meant to mention this at the start of class. This is the third chapter on magnetism. So we are having a test next week. So I probably should have mentioned that at the beginning of class. But so keep that in the back of your mind as we're moving forward through this week. We have a test next Thursday. So usually that means we can do like a Saturday review session, and we can have a second review session on Tuesday. So maybe I'll send out an email about that so that you guys can think about times that will work. Probably later at night.
Isn't next Thursday a holiday?
Is next Thursday a holiday?
Veterans Day.
Oh, so we have like a week off and then the test. Is that how it is? Let me pull up the syllabus here. I think I had it right in the syllabus. Yeah, so maybe you guys get a break and then a test. Is that right? Yeah. Oh, that's right. And I put like special topics here on the I put like special topics on the syllabus. Yeah, okay. Now it's coming back to me. Yeah, so there's the holiday week, and then we'll do the review. So we won't do review next week, actually. So next week is this thing I put here called special topic. I'm not exactly sure what that is like right now, but basically what I wanted to do was have like a lecture that kind of ties electricity and magnetism together a little bit more. So maybe what we'll do is we can even probably just get a lot of examples maybe that we didn't get a chance to cover kind of as we were going through. But the idea for this lecture was just kind of tie things in together, look at maybe some applications of, electricity and magnetism kind of working together, which I know there was like kind of a lot of examples on the homework, like mass spectrometer, right? You have like the velocity selector, which we did cover in class. Just kind of bring things together, right? So that was the idea for that. And maybe one thing which is kind of important that we haven't really looked at yet is Maxwell's equations in their differential form rather than their integral form. So that might be something we could also do on that day. And that's a much more natural way of looking at Maxwell's equations. So Gauss's law, the no magnetic monopoles equation, Faraday's law, and Ampere's law. You write them down in their differential form, and then you can solve them as differential equations. Obviously, we're not going to do that. That'd be a little bit above the math that we would want to do in this class, but certainly maybe we can write them down and take a look at them. And that is something that you actually should do headed into, what is it? I think chapter 33, which as far as the schedule is concerned, we don't have time to actually get into it. Oh no, excuse me. Actually, we can do that, I think, in chapter 32. Do we have 32 on the schedule? Oh, we have 31 on the schedule, but not 32. So we're going to cover AC circuits. So maybe that's what we can do, actually. That's maybe a good topic to cover. To tie electricity and magnetism together and talk a little bit about chapter 32 on that day. But I don't want it to be something that's not useful for you guys, because obviously you're going to have a test right after. So it's not going to be like we're going to cover a chapter that's not on the test. We will do stuff so that it's related to what you're already talking about. Okay, so don't skip out on next week. Actually, this is actually the perfect thing to cover for this day. So we'll take a look at the differential forms of Maxwell's equations, and maybe we'll show the existence of a wave equation for Maxwell's equations for the E and the B field. And that, of course, tells you that there's the existence of like radio waves, visible light waves, X-rays, gamma rays, things like that. So electromagnetic radiation. But we won't go too deep into that, and we'll try to keep things grounded in what we've already covered. So not much new. So it will kind of be a little bit of review, but a little bit new at the same time. Okay, so that's good. So we decided a topic on that. Even though we have the holiday, we can still try to do an extra review session before the third test. So maybe the Saturday of the holiday break is maybe a better time to do that. So maybe we'll do it that way. So not this Saturday, but next Saturday we'll do a review. Not this upcoming Saturday, but the Saturday after this upcoming Saturday. So yeah.
Professor?
Yeah.
I have a suggestion. Can you, for the test, for the next test, can you put the test practice like you did last test, like maybe put it earlier than
sure. Sure,
time?
yeah. I'll put it, so
we have
you
more
want,
time to practice.
you guys want me to put like 30 problems or whatever again, just as an extra 0-point assignment?
Yeah.
Okay. I did that for my other class. I did that for my my 205 class, but I saw a lot of them like weren't answering the questions in mastering. So if you solve so I know it's like some students probably print them out, right, and work on them on the side. It helps me if you guys actually answer them in mastering. So still print them out, still write out your complete solutions and everything, but submit an answer in mastering, so that way I have a sense of how many people are actually doing that. Just gives me confidence that when I put something up for you guys that you actually take advantage of it. So I don't feel like maybe I wasted my time creating that for you guys. So that is an important thing. So if I put up that assignment, which I will, just answer the questions in mastering, so I get a sense that you guys are all working on it. Okay. All right, so that's enough talk about the syllabus. Let's kind of get back to what we're doing over here. So we've answered this question. So we applied Go
One
ahead.
more question about the syllabus. I don't see the second holiday in there, so is that going to mess with what we have planned?
What's the second holiday?
Thanksgiving?
Veterans Day, or
No, Thanksgiving.
is Thanksgiving not in here?
No.
I thought that was the holiday. Oh no, yeah. When is Thanksgiving?
The 25th, Thursday.
25th. What week is that? So we're in week, what week are we in? With chapter 29. So we're in week 11, 12, 13, 14, week 14. Oh no, so we have stuff scheduled for week 14. Yeah, so what do we do about that? Chapter 30, that's a good chapter. That's AC circuits. That is definitely a good chapter that we want to go over. Oh no, inductance. Oh, you know what? Maybe we can do chapter 30 and 31 together. Maybe what I can do is I can just lecture the important parts from chapter 30 that we need to cover AC circuits, and then do some AC circuits. So just what we need from chapter 30 to do some AC circuits, and then do some AC circuits, and maybe do a combined like chapter 30 and chapter 31. Oh, but wait a minute. Hold on a second. Thanksgiving is on a Thursday, right? Thanksgiving is like Thursday, Friday?
Yeah, Thursday and Friday.
Oh, so we still have lecture that. Actually, I don't think Thursday is going to be or Thanksgiving is going to be a problem. So we'll still have lecture that Tuesday, right?
Yeah, but no lab.
But no lab, exactly. So let's see. Is it? I already put it in the. Oh, I have AC circuits listed for week 14. So maybe we'll have to back that up then. Okay, I'll just have to change the lab schedule. Okay, nothing about the course schedule changes then. So on week 14, yes, that's the week of Thanksgiving. So I will still put pre-lecture tutorials and some homeworks up, and a quiz. But yeah, you guys will have Thursday no lab. So I mean, I guess that means you'll have extra time to just work on those assignments. So that's what I would say. So I don't want to cut, if we don't have to, I don't want to cut a chapter out, because we already are technically not covering all of the topics that we're supposed to. We're technically supposed to cover all the way up to, is it chapter 33? No. We're supposed to cover up to chapter 32. So actually there's one chapter we're not covering. I'll cover it a little bit during that special topic though. Okay, so hopefully it'll be more of a complete coverage, and you guys will be ready for 223, which will start off with like light, refraction and reflection, and then diffraction, that kind of stuff. Okay, so any other questions about the schedule then? I think we already discussed that there's only 16 weeks, right? So there isn't going to be a final in the 17th week. Test 4 is going to be like a final exam. So just a heads up on that. Test 4 is going to be like a final exam. So I will put questions from every chapter on test 4, and that test will take the full amount of time. So I will give you the full 3 hours, because in order to ask more questions from different chapters, you guys are obviously going to need more time for that, right? So so just a heads up on test 4. That's going to basically be our final exam. Okay. Should we get back to what we're covering in this chapter now? Are we all good on that? There's a chat here. Yeah, it shows a break next week. Yeah, it's like Veterans Day, I think, right? Next week is Veterans Day. I don't know if we have any veterans in this class who doesn't necessarily be celebrating that, but it is a national holiday, so we will enjoy We will enjoy a day off and we will thank the veterans for their service, right? Okay, so let's go ahead and get back now. Am I sharing screen right now? I don't think I am I? Okay, so let's go ahead and share. Back to this example. Just recap this question. It's been a while. We did a lot of talking there. We got this 500 loop coil of wire. It's got a radius so we can calculate an area for it. It's placed between two magnets. The magnetic field is decreasing. And so we found that the induced field is going to be opposite to that decrease. So the induced field points to the right. And we can use the right-hand rule for that to determine the induced current and the direction of increasing voltage or increasing EMF. And we had to calculate like a magnetic flux for that, and the cosine of the angle came into play, and then we had to take a derivative, but only the magnetic field changes with time, so we only needed to take the derivative of B. Okay, hopefully that's a good recap there. The next question is another generator style question here. And these questions are super important. This is essentially what, so a lot of what we're doing in this chapter is essentially how all of modern technology works. It works based on Faraday's law, based on these induced currents and fields and things. So this right here is literally an electric generator or an electric motor, depending on the direction that it's running, whether you're feeding it electricity or whether you're spinning it to generate electricity. So basically our entire economy is kind of run on this idea of Faraday's law. So Maxwell's equations, once you have them, basically that tells you how technology is going to be, basically. Okay, so this question here, let me pull up the statement here. Where is this example? Right here. So we have an alternator here. So we have a simple alternator. I'll just leave the text in blue. Generates an EMF by rotating. The rectangular loop is rotated at constant angular speed, omega. The magnetic field B is uniform and constant at t equals 0, phi equals 0. How do I write that? Let's write it like this. Okay. Determine the EMF. All right, let's go ahead and fill in the blanks here. So we have phi here. That angle is 0. And then we have the angular speed omega. There we go. That's the one I was missing. Okay, so it says at t equals 0, phi equals 0. Look at how phi is being measured over here on the right side. So right now in the figure, phi is being shown as a 90-degree angle. But in the problem, they want us to look at when t equals 0, when phi is 0. Determine the induced EMF. Let me go ahead and do this question for you guys because we lost a little bit of time talking about the syllabus and everything there. So let's try and speed things up just a tad so we can make sure we cover everything. So what we want to do is we want to calculate the induced EMF. Well, the induced EMF is given by Faraday's law. So minus n d phi m dt. In this particular problem, the number of turns is 1, so we can forget about the n, right? We just have a single loop. And this single loop here is just taken to be this rectangle here. So sometimes you look at these problems, it's kind of unclear maybe what the area is. It's usually assumed that the area is, if I add in this dotted line right here, it's this rectangle right here. Just that rectangular piece is the area that you're working with. So sometimes maybe that is not so obvious, but that's what it is. It's always assumed to be that way. So the rate of change of the magnetic flux. Well, what is the magnetic flux here? Well, minus d by dt of what is the magnetic flux? Well, let's fill in what it is. If phi is 0, then that means all of the magnetic field is going through that area, right? So magnetic field is uniform, so it's going to end up being B times A. And we could put cosine of phi here. The problem wants us to specifically look at phi equals 0, but we need to actually include cosine phi in this expression. Can anybody tell me in the chat why we should include cosine phi here? Why do we have to include cosine phi even though we're looking at phi equals 0? Just quickly, anybody got the answer here for this question? So why do we include the cosine phi?
If it deals with a change in time and not just at one particular time.
I like your thinking about change, but not time. So phi is going to change, right? Phi at the instant when t equals 0 might be 0, but we're looking at the rate of change, right? We're looking at the rate of change. So phi here depends on omega. So omega times t is equal to phi, right? Okay, so we have to include the cosine there. This is the flux right here. This is the magnetic flux. So I put a little bit too much room here. Let's move that over. So we have to include the cosine here. When we take the derivative of this expression here, the magnetic field is constant. The area is not changing unless the angle changes, right? When the angle changes, you could think of that as being like a change in the area, but it's really just the angle here that's changing. And so what we end up with is simply B, A, derivative of cosine omega t. And what is the derivative of cosine omega t? Oh, whoops, I forgot my minus sign. This minus sign right here, we can't forget that. What is the derivative of cosine omega t? It's, hopefully you guys are thinking and you know what it is now. You've thought about it. It's omega times the negative sign, so this becomes positive, sine omega t. Did we all get that? Derivative of cosine is sine, or minus sign, I mean. Okay, so this is our expression here. So this is nice. This tells us how we generate AC current or AC voltage. Notice we have a sine wave here. So, well, I don't need to write equals again. I want to draw a graph. So we can write now that E of t is a sine wave. And what is the peak voltage? What is the max? What is E max? Well, E max is when the sine is 1. So BA omega. Right? BA omega. So this here, this value here is BA omega. This is E of t. This is t here. Okay. That's the induced voltage. So this is like a big result here that we're getting. That now we know how to design motors which have alternating current or alternating voltage. So this is super important for us moving forward here. So any questions about that? I mean, that was pretty straightforward, right? How do you get an alternating current? You just simply take a loop like this and you rotate it in a uniform magnetic field and you get a sine wave, right? And that's it. Now, there are some issues here with this. Namely, you can see some crazy stuff going on over here with these devices called brushes, okay? What these allow us to do is make sure that the polarity of the voltage is something that is in the direction that we want it to be in, okay? In this particular example here, the brushes are always in contact with the leads of the loop. Okay, so this signal here really is an alternating, I said signal. This voltage here really is an alternating voltage. It is going to go positive, it is going to go negative as this thing rotates, as the loop begins to turn. And on one rotation, the flux might be increasing. On another rotation, the flux might be decreasing, right? And so this thing really is going to alternate. Well, you can also set something up where, and let me go ahead and pull this image from the book. You can also set something up where you don't actually have an alternating current. You actually have a DC current. So it's always in the same direction. It's always positive voltage. So the current is always flowing in one direction. Now that's this here. So we can see here that the brushes are on the same loop, but there's like a gap in the loop there. And so as this loop rotates, those brushes will break contact and then make contact with the other side, thereby changing the polarity. The polarity was about to go negative, but you broke contact and switched the connection so that it stays positive. So what happens here for a signal like this, it's exactly the same analysis as before, but E of t on one rotation is going to be BA omega sine omega t. However, breaking contact and then reconnecting the opposite way forces the signal or the voltage to go, instead of going negative, it stays positive. And so you can encapsulate that behavior by simply putting an absolute value bar on the sine omega t. And so what you ultimately end up with is a signal which is basically absolute value of sine. So I can just go ahead and draw that here. So it goes like this, and now it would go down here like this, but it doesn't. It comes back up like this. And it would go down here like this, but it doesn't. It comes back up like this. So this is a DC voltage here. And so this, again, is E of t. And this is t here. And our max value is still BA omega. But now there's kind of an interesting bonus calculation we can do. What's the average EMF, right? What's the average value of the EMF? And so you'd have to calculate a time average of this signal here. This one, what's the average here of a sine? It's equally positive as it is negative, right? So if we were to do the average here, we'd just get 0. But for this DC style generator, when we take the average of the absolute value of sine omega t, we're not going to get 0. It's always positive. So our average is going to be in here somewhere, slightly below the middle, because you can clearly see that this thing, it's wider here. Or excuse me, actually it's going to be slightly above the average. Or, sorry, slightly above the middle. Sorry, I'm mixing up my words here. It's going to be slightly above the middle here, I believe, because it's spending more time at larger values because it's flatter at the top. And how do we calculate that? We do a time average. So a time average, and this is something we haven't seen in this class yet, but maybe you've seen it in your calculus class. We're going to do the integral of 1 over the period. So that's the time it takes for one period. And then we integrate the length of one period. So from 0 up to t. And then we just integrate that function, E of t. And we integrate with respect to t. And what this does is it's taking the average of the function over a certain time interval. We're just going to skip straight to the answer here. So we're going to integrate this thing from here to here, right? And so that's going to be a period of like 2 pi over omega, right? So t. I'll give you guys the information so that way you can calculate it yourself, like when class is over, if you want to go through that calculation. So you know, the period is 2 pi over omega, right? And the function here that we have to integrate is basically the absolute value of sine omega t. So you probably want to break that integral down. So it's going to be, 1/2 integral from 0 to t over 2 plus, sorry, 1 over 2t, should say 1 over 2t there, plus the integral from t over 2 to t. And maybe some of you who are more comfortable can do this calculation with just a single integral, and it is possible you could just time average over just one of these loops here. But this in principle is what you would do to time average a function. Sine has a period of 2 pi, so 2 pi over omega, technically 1 period, but absolute value of sine, you can clearly see the period is half of that. The period is technically pi over omega because it repeats every pi over omega. But that's the general principle there. And when you do this, this integral, you get BA omega over pi, if I'm not mistaken. Let me go ahead and double check that. Oh, sorry, I'm missing a factor of 2 here. You get 2BA omega over pi. So that's the average voltage there. Now, the book actually indicates that, of course, if you had many loops, if you didn't just have a single loop, then you could put n. You could multiply by n, right? So we could say n be a omega over pi. Okay, and same for up over here too. So now we have 2 signals. We have a DC signal and we have an AC signal for our voltages. So DC is E of t equals, and I know it sounds like I'm kind of like repeating here, but just bear with me here. It's kind of important, so it needs to be said 3 times, right? This is the way I like to write it to help me remember what it is. So here's me trying to help you memorize a formula. I write the omega first, and then I write BAN. And the reason I write BAN is because it spells ban, right? So it's just maybe a word you can associate with that signal. So omega ban sine omega t. And for the DC signal, you want to take the absolute value of the sine. Right? And we have the average, and I've just kind of written it right above us here. So, and again, I'll write it as 2 omega ban. Probably actually the best way to think of it is to write it as 2 over pi. 2 over pi is the time average of sine or cosine over 1 period. So 2 over pi times omega ban. Okay, and that's the average there for that one. Now for AC, we have, again, it needs to be said 3 times. We have omega ban sine omega t, and there is no absolute value this time because it is an alternating current or an alternating voltage, and so it does go negative. The average of an AC signal like this is 0. It's a sine wave, so the average is 0. Now there could be alternating currents, alternating voltages where the average is not 0. But in this case, you take the average of sine omega t, which is allowed to become negative, and you get 0 because it's equally positive as it is negative. When you take the average of the absolute value, it's only ever positive. So the average is going to be positive. It's not going to be 0. Okay, any questions about that? Do we have any questions about that? Now we're ready to calculate something for this particular loop, and that is namely the motor's back EMF. So now we want to calculate what's called back EMF. I'll go ahead and type this up just to get it written down quicker, since we are on a time crunch a little bit, I think, at this point. So calculate the motor's back EMF, induced voltage opposing the generated voltage due to the rotating loop. Okay, so let me read a little bit of this statement here. So the generator that we have here is a direct current generator. Let me scroll up. Okay, maybe it's, I'm dragging the text box on accident. There we go. Let me just scroll up for a second and talk about this motor real quick. So this is a DC motor. It's a DC generator. The EMF always has the same sign. That's what DC means. Always has the same sign. Alternating, it goes plus, minus, plus, minus, plus, minus. Here we have the same sign always positive. The thing at the bottom, the brushes which are making contact with these kind of circular rings, that's called a commutator. That's what allows the voltage to stay the same sign. It breaks the connection and then reconnects in the opposite direction so that the minus becomes a plus. When we do that, we get, again, a DC voltage, and it's always the same sign. Now, in practice, the signal is not going to be the perfect absolute value of a sine omega t. Because you're breaking the connection, you're going to have some kind of some fuzziness in the signal, and maybe you could pick that up on an oscilloscope in the lab. But the motor's back EMF is an EMF which is induced by the changing magnetic flux through the rotating coil. And that is what we've just calculated. Actually, yeah, what did I say here? Oh yeah, I worded this very strangely, actually. Why did I word it like that? Let me delete this. Opposing the generated, no. Sorry, I didn't mean opposing the generated voltage. I meant opposing I just got a little bit confused while I was thinking about it. Let me rewrite that. So calculate the motor's back EMF, the induced EMF opposing the changing magnetic flux due to the rotation of the motor, of the loop. Okay. So sorry about that, I messed that up, but I don't think I gave you guys enough time to even write that down anyway. So now you can go ahead and write that down. So calculate the motor's back EMF. In other words, the induced EMF opposing the changing magnetic flux due to the rotation of the loop. That's what we've just done here, okay? But let's go ahead and plug in some numbers and really get a feel for how much voltage we can even generate from something like this. Okay, so if we take the number of turns to be 500, and we take the length of each side of the coil to be 10 centimeters, and we take the uniform magnetic field to be 0.2 Tesla. I don't know what it is with this book and their obsession with 0.2 Tesla. Maybe that's like a standard magnetic field size for a lot of like motors. I don't know, but it seems like they use that value quite a bit. And at what rotation speed? So here's the question. At what rotation speed, what value of omega will we get an EMF average, which is equal to 112 volts? So something similar, like a similar voltage maybe you might get from the outlet. Of course, your outlet is AC, alternating current, not DC. So this is the question here. So calculate the angular speed that we need in order to get this average EMF. Go ahead and start working on this problem right now. I will go through it a little bit slow. If you want to go fast, go ahead and go through it fast. Step number 1, identify the equation that we want to use here. we want to use this one. Average EMF is 2 over pi omega ban. Solve for omega. If I solve for omega, I have pi over 2 times EMF average, and I'm going to end up dividing this thing by ban, B-A-N. Writing it a little bit neater, I have this. Go ahead and write your answers in chat if you're quick enough to beat me to it. The area here is given by L squared, the side length squared. So I'll go ahead and make that change right away. Switch over to purple now. I'm plugging in numbers. We have pi, we have 112 volts. 2, we have a 0.200 Tesla. L squared, L is 0.1 meters. We square it to get the area. Number of turns is 500 here. Number of turns has no units, that's counting, right? So 500 times the 0.2 here is going to give us 100. And then this 0.1 squared is going to give us 1/100th. So these terms cancel, those three right there. And what we end up with is 112 times pi over 2. Which is a numerical value roughly of 176 radians per second. Remember, angular speed is measured in radians per second. Now we can convert that to revolutions per minute if we multiply by 60 and divide by 2 pi. Which gives us 1,680 revolutions per minute, which is an insane number of revolutions per minute, right? That's fast. This thing is rotating really fast to get us this 112 volts. And there are a couple things that you can do to improve upon the design of this motor, or excuse me, actually technically this is a generator here, but a generator ran backwards is a motor. A motor ran backwards is a generator. In the case of electricity and magnetism, in any case, if you run your car engine backwards, that doesn't necessarily make sense, right? Okay, so its improvement upon the design could allow us to get the same 112 volts with far less revolutions per minute, right? But that's just a design problem. Now, since I have mentioned the two types of motors and we've got an equation that tells us the voltage given in terms of a sine wave, let's actually talk about the wall outlet here. So the wall outlet has something, and this is related to the design of these generators here. Your wall outlet has something which is called three-phase AC. Now what that is it's three different signals which are out of phase with one another. So you have a sine wave like this one, and this one is going to be proportional to sine omega t. And then you're going to have another wave which is 120 degrees out of phase. Now let's approximate here. This is about 60, this is another 60, and this is, of course, your 180, right? And so this sine wave would begin here. And let's hope I can make this look decent. Should cross right around there. This guy right here is going to be proportional to sine omega t, but there's a change in phase here. So sine omega t plus, or actually rather it's shifted forward if this is the t-axis. Sorry, this is the omega t-axis, make things easier. it's shifted forward in amount 120 degrees. Okay, and then of course I said 3-phase, not 2-phase. So we get a third signal in here. Maybe we'll do it in green. And here's 60. There's another 60. There's our supposedly our 2 pi right there. And so this one would begin here like so, coming up like this, and then it's going to come down over here and then come back over here. We can kind of continue it back this way, so come out this way. We continue the red one as well. And now here we have what's called 3-phase AC. This one is proportional to sine omega t minus 240 degrees. And now why would we want to do something like this? Well, the sum of these 3 signals is in fact 0. You can verify that sum yourself using the fact that sine A plus B is equal to, what is it equal to? Cosine A sine B plus cosine B sine A. You can verify that the sum of these 3 signals is equal to 0. Where's my mouse at? So the sum of these is going to be equal to 0. That's why we use 3-phase AC. To get a 3-phase signal, by the way, this is not included in the book. I am doing this off of memory here, so if I make a mistake, sorry about that. Just maybe you can look it up and let me know if I made a mistake or something. But yeah, in order to get this 3-phase signal, what you can do is you can set up some magnets like this. And these magnets are all 120 degrees rotated from each other. Or rather 60 degrees. The angles between each of these is 60 degrees. And each set of the magnets here, if you go, if you rotate through these magnets, because you're going from one direction of the magnetic field, like let's say our coil is here like this. Oh, sorry. Oh yeah, this is a mistake here. So let me get the eraser here so it's a little bit easier. I should have alternated north-south, north-south. It would make a lot more sense if you rotated from north to south, because that would be more magnetic flux, right? I'll let you think about why that would be more magnetic flux. This one being south is fine, but let me write it neater. And then this one here should be north. Okay, and so when the coil is like this here, you can see we're in, we have north pole coming into it, right? We have north pole coming into it. And if we rotate it, then we would have south pole coming out of it. So that would be a big change, right? That would be a big change in the magnetic field. And the angle between north and south here is 60, but the angle between 2 north poles is 120 degrees. So that's why this is going to be 120 degrees out of phase. So you have this kind of 6 magnet setup here where you rotate a coil inside of these magnetic fields, the magnetic field here in the middle, and you ultimately end up with a, oh, and this is actually an interesting fact here about this. If you actually calculate the sum of all of the magnetic fields in this region, the component that is inside of the the component that is inside of the solenoid, I believe, is always perpendicular to the face of the solenoid. So you get maximum flux, if I remember correctly. I have to think about it. I have to get back to you guys on that one, actually. There's some nice properties to a motor like this, or sorry, a generator like this. Okay, so that's a little aside on what's going on in your wall outlet and what the power company is doing. They're doing 3-phase AC. So the sum of all of these signals is 0. So obviously, if your wall was getting all 3 of these signals, there would be no power coming out of your wall, right? So your home is actually getting about 2 of these waves. You're not getting all 3 of them. So you're maybe getting the blue and the red, and other people on your block may be getting blue and red, or maybe they're getting blue and green. So different houses will get different pairs of these waves. But the nice thing is that the signal coming back to the power company is the sum of all 3 of them. And so it's 0. So it's a really nice property there. Okay, so any questions about that before we get to the next topic? So the next topic we're going to take a look at is what's called in the book a slide wire. There's a couple interesting properties for this type of system here. So let's go ahead and take a look at it. It's called a slide wire. Sometimes you'll see like rail guns with this kind of schematic. But essentially what it is we have a situation where we have some wires here like this. And then we have a bar which makes contact with those wires. And this is basically the slide part. So this thing is allowed to slide from, right to left or left to right, depending on what you're doing. So in this situation here, let's go ahead and draw in a magnetic field here. We have a uniform magnetic field over here as well. So everywhere in space, we have this magnetic field, B. We'll take the area vector to be into the board as well. So this is the area vector for this loop here. And what we're going to do is we're going to set this wire in motion. Okay, we're going to set this thing in motion. We're going to have it move in this direction with a velocity v. I want to see what happens here. Well, if I move this thing with a velocity v, then I'm increasing the area of this loop, right? So if I increase the area of the loop, how much is it going to increase by? Well, it's going to increase by an amount v dt, right? This is delta x here. That's how much the length of the length here is going to change. So this is the length, right? How much does the area change? Well, delta x times maybe they used the letter L here for the, let's call this the width. W for the width. And then we have here the length. So this is the length of that rod. So if it changes by an amount delta x, this is the extra amount of area that we have here, right? So this is our delta A. And delta A is going to be V dt, that's the extra width, times the height or the length here, L. So L V dt. I wrote delta A, but really I should have wrote dA. Sorry about that. So make that a dA. So dA equals LV dt. All right, so the magnetic field is not changing. So if we want to go and calculate the magnetic flux here, the magnetic flux is simply going to be BA cos theta, right? Let's actually write the integral here. So integral of b dA cos theta. Cos theta is 1 because the area vector here and the magnetic field vector are in the same direction, drawn in the figure here on the left. So the area vector and magnetic field vector are in the same direction. Magnetic field is constant with respect to the area. So we end up with integral of dA. Now, dA, when you integrate it, is just A, the area of this thing. So this is simply B of B times A, where A could be like length times width. Now, the area is changing. So when we take the derivative of the magnetic flux, then we'll have the derivative of A, which from here, dA dt is equal to LV, right? So the derivative of the magnetic flux with respect to time, the magnetic field is not changing, so it's B times dA dt. And of course, dA dt is LV. And we get an answer that we've seen already. And actually, I calculated something like this for you guys already called motional EMF, which is actually in this chapter. So I did that, I jumped the gun a little bit on that, but that's okay. So we've seen this kind of calculation once already. Motional EMF has to do with the forces on charges in this bar here as it moves in a magnetic field. If it's a conductor, it will experience a like some polarization. Okay, so we've calculated the EMF here. What's the direction of the EMF? Well, the flux is increasing. Since the flux is increasing, Faraday's law says that E is equal to minus d phi dt. By the way, this here is the EMF, the absolute value of the EMF. So the minus sign here tells us we have to oppose the change. So if I slide this thing out and increase the area, well, what's going to happen is the induced voltage and the induced current and the induced magnetic field want to oppose that change. Okay, so we need to think of a way where we would induce some kind of current that would reduce the amount of flux, since we're increasing the flux. Well, if this thing is moving to the right, then that means that the flux here in this loop is increasing, right? We're going to have more crosses in the area if we move this thing to the right. So that means we should generate a current which is going to give us induced magnetic field in the opposite direction on this side here. So the magnetic field that's induced should be in this direction. That would oppose the change, right? In order to get that induced magnetic field, we use the right-hand rule. So your thumb is going to point in the direction of the current on the wire, on the blue conducting like rod. That's basically a wire here, a slide wire. Okay, so if I'm using my right hand, I see I can get my fingertips to point in the direction of B induced like this out of the screen, and my thumb points up. So the induced current is in this direction here. So this is the direction of the induced current. I induced. Oh, whoops. I induced. Okay, so I induced is going this way here. And interestingly enough, of course, if it's going up here, it's also going to the left here. And if you do the right-hand rule there, the magnetic field is also in this direction, right? Which makes perfect sense, right? So, and then if it's coming down this way, again, right-hand rule, the magnetic field induced is going to be coming in this direction. So this definitely opposes the change in magnetic flux. And now we understand the direction of the voltage now is going to be in that direction. So if I wanted to like draw a battery here, which is the EMF source, then I could draw it like this. I could say, okay, this way is positive and this way is negative. So positive, negative, EMF, and that EMF is BLV. Okay. Does that make sense? Give me a thumbs up if that makes sense. I got a fly flying around me. Okay, so I think that's pretty much everybody. All right, so if we have this induced EMF here, and we got this induced current, this induced magnetic field, right? Now what? What kind of questions can we answer with something like this? Well, we could think about this kind of system maybe in reverse, and that would be called a railgun. So I could apply an EMF, and that EMF would generate a current which flows in this circuit here. And since there's a current being forced to flow in the circuit, then obviously there's going to be a force on this current carrying wire, right? And that force would drive this this projectile now. This slide wire is now a projectile. You're gonna want to shoot it off like a gun, right? Like a rail gun. So that's the kind of question you might be asked on like a homework. So let's take a look at maybe something like that. So we'll come over here, and the direction, I gotta make sure I draw the directions right on this. So if I put my voltage source like this, and actually I'll go ahead and make this a delta V now, since it's not being induced. We'll add in a resistor too for good measure. Actually, I should extend this a little bit. That was a terrible line. This fly is kind of annoying. Okay, so there we go. We've got a picture now. And now I have to think for a second. Okay, the current's going to be going this way. So we want the magnetic field to be going into the board. Okay, so there's our magnetic field. Current is going to be flowing in this circuit, driven by this voltage source here, by this power supply or this battery that we have in the circuit. Assume that this bar has negligible resistance, okay? And what we want to do is we want to calculate the velocity of this projectile, okay? Now, in order to calculate the velocity, we have to be a little bit careful. If I drive the current like this thing becomes a current carrying wire. So there's a current flowing in this thing like so. So the force on a current carrying wire, by the way, this thing will have length L. This thing will have like a width W, right? The force on this wire would be given by ILB. Everything is perpendicular here. So we have a force on this wire If we use the right hand rule, so right hands have to point down in the direction of the current. So point your fingers down, curl them into your screen, and you can see that the force is to the right. Usually use red for forces. So we have a force here to the right, which is ILB. Now, if we have a force like this, well, at some point, since this thing is accelerating, forces, so we don't want to get too complicated here, but we do need to talk a little bit about this next bit here. So force is mass times acceleration, right? And so this thing is going to speed up, okay? Which means V is going to increase. As V increases, we just calculated that the flux depends on V dt, right? So at some point, there's going to be a time in which the force due to the induced current or induced voltage is going to equal the force due to this thing here. So the current on a current, the force on a current carrying wire. Okay, so let's try to take a look at that. So if we have this kind of situation here, then we force the current to run this way. There's a force on this thing, so it's going to accelerate in this direction. If it accelerates in this direction, then of course the flux changes. And we just calculated that. At any instant in time, the change in flux, well, actually, maybe we should actually redo that calculation just to be safe here. So this is the integral of B dot dA. B is not changing, B is constant. We can pull B out. We can rewrite this thing as B dA, no cosine theta because it's 90, or sorry, it's same direction here. We can make the area vector be in the same direction. We can pull B out, so integral dA, and the area is the area is width times length, right? So width times length. Length doesn't change, but the width will change. The width is going to depend on the velocity here. So the width is going to be like an initial width. So BL, like some initial width, let's call the initial width W, plus V times delta T. Okay. Let's maybe put a subscript of a 0 here. That's like the initial. Well, actually, as a matter of fact, maybe that's incorrect here. We have an acceleration here, so we probably should be really careful. We should say W0 plus integral of V dt. Let's be extra careful here. The velocity may be changing at certain instants in time, and then will taper off to some terminal value where it's constant. Okay, so now if I want to take a time derivative of this thing, so d phi m dt, oh, I did q, d phi m dt, magnetic field is not changing, the length is not changing, the initial width doesn't change, but the derivative now will act on this integral. That's fundamental theorem of calculus here. So even when the velocity is changing with respect to time, we still end up with this expression here, BLV. Okay. So this is the going to be the induced voltage, basically, if we were to take a magnitude. So the magnitude of the induced voltage is BLV. Of course, that's going to be in the opposite direction, right? So that's going to be in the opposite direction to this current here and this potential difference here. Okay. And now, if we were to calculate from this information here an amount of induced current, the I induced here would be given by BLV over R. That's the induced current. The current over here, though, is delta V over R, right? So the current over here is delta V over R. That's different. The current here is BLV over R. And now we can clearly see there's gonna be some sort of balancing here. I induced is delta V over R. If this guy is gonna accelerate, right? It's gonna accelerate up to some certain velocity. At some point, this thing is gonna reach a state where the induced current here, based on this velocity, if the velocity continues to get bigger and bigger, we can clearly see the induced current is going to get bigger and bigger, right? As the induced current gets bigger and bigger, we have an opposing force, which is going to be I induced times L times B. Our applied force due to our applied voltage is just this I times LB. Just give me a thumbs up if you guys are following where I'm going with this. Is what I'm saying making sense here? So we have an applied voltage source, so there's a force on that wire due to that applied voltage. So that's the current I. And then we also have an opposing force here, which is due to the induced current, which is going to be in the opposite direction. As we just showed in the previous problem, we have the same setup, except this time we actually have an applied voltage. All of the induced properties are still in the same direction as before. So we have an opposing force due to the induced current. So I didn't get a single thumbs up, so I'm guessing all of you guys are lost right now. So let me just explain it one more time. So we have an applied voltage which drives current in this circuit. What's going to happen? Faraday's law. Faraday's law is minus, change in flux over change in time gives rise to an opposing voltage here. It opposes the change. So what's going to happen is, due to Faraday's law, we're going to have an opposing force in this direction. This is our applied force. The applied force due to the applied voltage. At some point, these forces are going to be equal, and the projectile will move with constant velocity. Does it make sense? Okay, so is everybody lost right now? Can you guys just let me know in the chat? So I'm not seeing any thumbs up. So are we lost? Do we need to back up? Maybe I didn't explain something very well. Hello? Can you guys hear me? Okay, nobody's given. Okay, so I guess I should back up and explain. Is that correct? Somebody say in chat, do they want me to explain this again? Maybe I didn't do a good job this first time here. So let me just kind of walk through it again. So we have a system where we're applying a voltage here. So hopefully this figure makes sense. So we're going to have current flowing in this circuit. Okay. This current I here is the current that's flowing in the circuit because of the battery that we have connected to the circuit. There is going to be an induced current, which is in this direction, in the pink direction. This is going to be the induced current. That's because of exactly what we saw before, right here. If this thing moves to the right, we induce an upward current when the magnetic field is into the page. So if this thing moves, the flux changes, so there's an induced current upward to oppose the change. That was what we were doing with these red dots here. That's going to be the induced magnetic field, so that's going to oppose the change. Okay, so if we oppose the change like that, and we have an induced current like that, then there's going to be an opposing force as well. And that opposing force is due to the induced current. That's what we just went through here. So we repeated the calculation here for the change in magnetic flux because we know we have an acceleration. Because we have an acceleration, we don't necessarily know how the velocity is going to change in this formula here. Now, it turns out the fundamental theorem of calculus that the derivative undoes the integral, right, saved the day, and we still have the same formula, BLV, although V now changes with respect to time. So this is now a time-dependent velocity. So here we have V depends on T. That's the difference here, but we didn't write it explicitly because what's going to happen here is because of this induced voltage, we have an induced current, and that induced current is going to give rise to an induced opposing force here. So we can write that the force on the wire due to the induced current is I induced times LB. And our applied force is ILB. Just what we started with here. Delta V over R is I, right? So that current I there is going to give rise to a constant applied force. So this force here is constant. And this force here is increasing. And this force is going to increase until it equals F applied. It's going to increase until it equals F applied because it depends on V. And V is given by the acceleration, which is given by Newton's second law. So we have F applied minus the opposing force is equal to mass times acceleration here. And this equation tells us for the applied force, it's ILB. And all of these quantities here are constant. So this is literally just a constant term in this equation, minus I induced LB. And I induced changes with time. So the acceleration over here is a function of time. The velocity is going to be a function of time. Okay, that's because the I induced depends on the velocity. Let's plug it in. ILB minus I induced is BLV over R times LB equals MA. Okay, and again, V is a function of time here. Can we see that this is a differential equation? Acceleration is dv dt, right? So m dv dt. We could integrate, we could literally integrate this equation and get an expression for the velocity as a function of time. And then we could take its derivative and find the acceleration as a function of time. That's something we can do. I'm not trying to do anything difficult here, but maybe I've confused you guys a little bit with my explanation there. Maybe I wasn't quite clear on what's going on. I want to do the easy thing, which is calculate the terminal velocity. So I want to take a limit on this equation. I want to take a limit as delta t goes to 0. As t goes to infinity. What am I saying? I want to take a limit as t goes to infinity. Because as t goes to infinity, the acceleration goes to 0. So this term goes to 0 in the limit. Okay, that term goes to 0 in the limit as t goes to infinity. The velocity becomes constant in that limit. So what we have is ILB minus b squared L squared V over R is equal to 0. Okay. And I could multiply both sides by R, and then what I'll end up with is delta V times LB, and then I can add this term to the other side, B squared L squared V. So so delta V here is I times R. Is everybody following me? Give me a thumbs up if you're following me on this step here. Okay. All right, good to see. All right, so we can cancel an L and a B, right? Okay. And what we see, surprisingly, maybe it's a surprise, maybe it's not a surprise, I think it's a surprise, is that the velocity is going to be given by the equation delta V equals BLV. It's almost like we just went through this challenge problem just to figure out something that maybe should have been obvious, that the velocity is going to be given by the applied potential difference and the magnetic field that's already there. So a complicated process to get a simple answer, which basically tells us that the magnetic field times the length of that slide or the projectile, if it's like a rail gun, is B times L divided by delta V. But this is the applied voltage, not the induced voltage. This is the applied voltage, not the induced voltage. Before, if we scroll on over, it was the applied voltage, right? It was the induced voltage. See here, it was the induced voltage, right? So this was purely from Faraday's law. We got that the velocity of the projectile there was connected to the induced voltage. If you remember in this problem here, we are the one moving the slide. We give it a velocity. So maybe what we do is we kind of like push it, right? And then it starts moving with a velocity V. Or maybe we pull on it with a constant force. And we pull on it with a constant force, it's going to end up with a constant velocity in the long time limit. If we pull on it with a constant force for a long time, we just proved that actually with that differential equation. We just proved that if we pull on it with a constant force, it will have constant velocity in the limit. So if this thing is moving with constant velocity, the induced voltage is directly proportional to the velocity. So this right here told us whatever the velocity is that we make this thing move with, that's going to induce a voltage. And the connection there is that it's the induced voltage divided by BL. Right? So kind of what we got over here. Oh my God, I made a silly algebra mistake here. I accidentally flip-flopped these two terms here. So the BL should be on the denominator. The delta V should be on the numerator. Sorry about that. There we go, fixed it. Fix that up in your notes real quick. Fix that up in your notes. So the velocity is equal to the applied voltage divided by the magnetic field times the length. So like this. Okay. Seemingly a hard problem for a simple answer there. I don't think it's too difficult though. Review that if you're a little bit confused on that. I think the math here makes pretty good sense here. We just kind of calculate the change in flux here for the situation, and we end up kind of with a lot of familiar formulas like force on a current carrying wire, induced voltage in terms of the velocity, etc. Balance the forces, Newton's second law, right? Newton's second law always applies. In the long time limit, in other words, the limit as t goes to infinity, the acceleration will tend to 0. The reason for the acceleration going to 0, of course, is because this current here depends on the velocity. So if this velocity wasn't here, taking this limit would mean nothing. There would be no real limit to take. In fact, the acceleration, might go to infinity as we take the limit as t goes to infinity, or it could go to 0, or it could go to some constant value. But since the velocity is here, and these two forces are working against each other as the velocity increases, then the acceleration must go to 0 there. So that's a nice tool to have in your tool bag, taking limits on differential equations to get limiting behavior. Okay, so let's go ahead and maybe do a calculation with this. Actually, I don't know if the book has a numbers example here, but maybe something we can do. Actually, there is an example here. It's a symbolic example. So get an analytical answer with symbols, and that is to calculate the power. How does it phrase it? Find the rate at which energy is dissipated in the circuit. So find rate at which energy is dissipated. Whoops, I always do that. Which energy is dissipated in the circuit. Can you guys tell I finally got a new mouse in the circuit? So find the rate at which energy is dissipated in the circuit. Well, just to remind you, power is the rate at which energy is dissipated in the circuit. And the only thing dissipating power in this problem is the resistor, right? So the power dissipated in the resistor, of course, is given by I times delta V R. And that, of course, is given by, I should subscript IR. These are functions of time, by the way. So IR squared times R. Okay, I'll let you guys work on that. Do you guys want to work on that solo, or do you want me to put you in groups? Let me know in the chat, groups or solo. One person has responded. I'd like for more people to respond. Please give your input in the chat. You can directly message or you can message publicly. It doesn't matter. Do you want to work on this in groups, or do you want to work on this solo? We can maybe add one caveat to this problem here. Instead of looking at the power dissipated as a function of time, maybe we can look at the steady state power dissipated. So what is the book actually? Everybody wants solo, so go ahead and start working on this problem. But let me clarify one thing here. So right, that was the question that I had there for myself. So obviously we have to do work to move this thing. The net force is 0, so the net amount of work here is 0, but there's power being dissipated by the resistor. There's also power being supplied by the battery. So what they want you to calculate here is the power dissipated by the resistor due to the current supplied by the source. So clarify a few things here. So they want us to take the current in the resistor to be equal to the current that is supplied. So in other words, the power dissipated by the resistor at t equals 0 is kind of the idea here. So ignore the effects of the induced current. So ignore the effects of the induced current here. That is not the correct answer. Put it in terms of, I guess maybe I shouldn't say that is not the correct answer. I should say, put it in terms of the quantities that that we're interested in, like the magnetic field, the length of the slide, things like that. So, I mean, technically, yes, that's true, but that's not really what we're looking for. So what is I here in this case? This particular problem, yeah, okay, so the wording for this problem is pertaining to the previous example, not the one that I've written here. So I is given in terms of this expression here, so B L V over R. You can get that from this equation here, so, oh, but wait a minute. Oh, this would be in the steady state limit, not the t equals 0. Okay, yeah, so maybe okay, let me just go over this question myself here for a couple different cases. Okay, so I guess you could write a couple different things here. So one thing you can do is you can look at P at t equals 0. At t equals 0, the current in the circuit squared times R is the power dissipated by the resistor, okay? And this is the current at t equals 0. This is the total current. So this is I from the source, which is delta V over R, delta V over R, plus I induced, and really maybe we say minus I induced. And we square this. And I induced is 0 at t equals 0. And actually, oh no, yeah, that works. Yeah. So I induced is 0 at t equals 0. Okay, we could also look at maybe perhaps the power and just squaring this thing out. I mean, I guess delta V squared over R is fine. Just writing it as I squared. R is also fine. There's a couple different ways you could write this. Now, looking at power in the limit as t goes to infinity, as t goes to infinity, what's going to happen is this thing is going to be moving with constant velocity, and the amount of induced current is equal to the amount of current supplied by the battery. And so the total current is actually 0. So delta V over R minus I induced quantity squared times R, but I induced is going to be, where did we write it down first? I induced is going to be BLV over R, BLV over R. But in the t goes to infinity limit, delta V is also going to be BLV. So delta V will tend to BLV in the limit as t goes to infinity. Okay, and so what you ultimately end up with is 0 for the power dissipated by the resistor in the limit as t goes to infinity. Okay, so the book actually asks in its example not this question here. This is a question I came up with. This whole example here, I just wrote this from scratch. This example all the way up here. So let's go back and look at the example in the book for a second, which is this one, where there's no source. So I'll redraw this circuit here with no source. Okay. So here's the circuit, like this, and we have this here. Here's our area, or sorry, our rod. Okay, there it is. And this thing has a velocity v that we've given to it. And there's an induced current, an induced EMF, induced magnetic fields, and so forth. And in this case, we calculated the induced the induced potential difference, induced EMF, we calculated it to be BLV, right? And so if we have a resistor here and current flowing in this circuit, if I remember correctly, the current flows this way, then ultimately the power dissipated by this resistor can be calculated. And that power is given by, again, the expression I squared times R, and I is going to be E over R, quantity squared, times R. E is BLV, so BLV over R, quantity squared times R. And of course, then this is going to be B squared, L squared, V squared over R. Okay. So if you want to know the power dissipated by a resistor for a situation like this, where there's no applied voltage, the applied voltage here is 0, but there's an induced voltage, and the induced voltage looks like this. There's an induced voltage, and its magnitude is BLV. Then that's the formula right there. B squared, L squared, V squared over R. Okay. So make sure that you understand both of these examples because they're kind of important examples here. So we have the case where there's no applied voltage, and then up here we went over this kind of longer example where we have an applied voltage, but we also took into consideration the induced voltage for that case. Okay, so two important examples there. Any questions about that? Any chats here? Give me a thumbs up if you're good, if you want to go to the next thing. Okay. We already covered motional EMF, and Lenz's law is something that we've seen already. Let me just write down Lenz's law. Lenz's law means induced quantities always oppose changes in the ambient quantities. Okay, that's Lenz's law. So figure out how the ambient quantities change: current, magnetic field, voltage, all of those things that are already there. Figure out how they change, and then the induced voltage, current, magnetic field will oppose that change. That's Lenz's law. We've been using it, right? We've done it in the lab. We've done it here as well. So that's Lenz's law. I've written it down for you. Let's go to the next topic. The next topic is motional EMF. I've already covered this. This is when you have a conductor which is moving in a magnetic field. It gets polarized, and the formula that you get for a rod moving in a constant magnetic field is E equals BLV. So if I have a magnetic field like this, again, this is basically identical to the slide problem from before. If I have a rod like this moving in a magnetic field, then there's going to be a potential difference, plus at the top, I believe, yes, minus at the bottom for this setup here. And that is an E equals BLV. Same formula that we've seen a couple times now. Well, that's good because that helps you remember it. All right, so that's motional EMF. There is a general form. There's a general formula for motional EMF. And it comes about by taking a look at current elements kind of in a Biot-Savart kind of style, although not quite exactly in a Biot-Savart kind of style. But you can take a look at it in the book. Probably the best explanation I can give is if you have a force which is purely magnetic, it's Q equals V cross B, right? That's the Lorentz force. And you can look at how much work is done in moving charges in that magnetic field as the integral, so there's no integral yet. It's the force dotted with some line element, right? So this is like by definition what work is, right? And I've written dl instead of dr because we always see dl when we're doing magnetism. So F dot dl, well, I can redefine this expression here. I can divide this by Q, and that gets me dE, right? Remember, delta V is work over Q, right? There may be a minus sign in there, but we'll sweep the minus sign under the rug for now, okay? Because we can always use right-hand rule and things like that to find the direction. I just want to get through this quickly so we can cover everything before we run out of time. So then you can integrate the expression, right? Well, plug in for the force. It's V cross B, dot product with dl. Put that thing in parentheses. And so if we want to know the EMF, we have to integrate over a closed loop, right? Remember all the way back from our definition of the potential difference, we always integrate on a closed loop like this. So this is our general expression for motional EMF, okay? So it's written in terms of the cross product of the velocity and the magnetic field coming from the Lorentz force. And if you remember the way we derived this expression here, we looked at, okay, there's a magnetic force in this direction and an electric force in this direction, right? Fe, Fb, or Fm, I mean, and there's like a positive charge here in the middle if this thing is moving to the right. And so that told us that QE was equal to QVB. And E we wrote as E over L. Cancel the Q's actually, cancel out the Q's, equals VB. And we end up with the expression E equals VBL, right? That's our motional, or BLV, right? Whatever you can remember easier, BLV maybe, since we've been writing it more. But there you go, that's the idea right there, okay? So that's motional EMF in a nutshell right there. There's the general expression. Okay, let's go ahead and move on. Take a look at the example problem for general motional EMF. It's a nice problem with a disk, and the disk is rotating. So that's a little bit of a, maybe it's non-intuitive what's going on there. So really take a look at that example. Might help you on a homework problem. Okay, the next thing that we want to do is write down a general expression for Faraday's law. So we've been saying E equals minus N d phi m dt. But as I just reminded you, we can write dE here in terms of the work, right? So, and then we can take a look at electrical work, and we can write E as, what is it again? It's minus a closed loop integral, closed loop for, if this is delta, then what we have here is correct. So closed loop of E dot dl. I'll use dl because we're doing the magnetism. We've been using dl a lot. So that's how we can rewrite the EMF here. And of course, that's got to be equal to minus N d phi m dt. So we can also rewrite the right hand of this expression as minus N d by dt. And the magnetic flux can be written as an integral B dot dA, right? So this is the full integral expression for Faraday's law right here. If we just take this, I'll take out the middleman here, so to speak, and we'll move this over. Boom, there is the expression for Faraday's law in its integral form. Okay, so we can see we've got integrals on both sides. In fact, we have different kinds of integrals on both sides, so we can't cancel the integration unless we can switch one type of integration to another. That's called Stokes' theorem. And actually, we'll do that during the special topics lecture. Okay, so if there's no n there, then obviously we could just ditch the n, right? So if we don't have multiple terms, just get rid of it. Okay. All right, so the next and super important topic I want to cover is the generalization to Ampere's law. And what we need is a couple pictures for that. Did everybody have a chance to write that down? We need a couple pictures for this. Imagine we have a capacitor. And that capacitor has current flowing like this. We know from our investigations into the magnetic field of current carrying wires that the magnetic field by the right hand rule here, thumb pointing to the right, fingers curl out of the page at the top and they curl into the page at the bottom. We know that the magnetic field there is given by the expression mu0 I over 2 pi r, where this distance here is r. Okay, we can apply Ampere's law to get that answer. Ampere's law says take a closed loop like this and go around it in this way, kind of in the same direction as the magnetic field. And the integral over that closed loop of B dot dl is going to be equal to mu 0 I enclosed. Well, the enclosed current is just I in this case, so we don't need to consider that. The integral B dot dl, well, this right here is going to give us 2 pi dr, and B is just going to be constant. And if we integrate over the entire loop there, well, that's taken care of by the 2 pi. And so we integrate this to get an r. So what we end up with is B times 2 pi r equals mu 0 I. And then we divide both sides by 2 pi r, divide by 2 pi r. Okay, so I've reminded you how we get that answer. I won't do it again. All right, well, Faraday's law says that if we have changing magnetic flux, we should also have an EMF, right? Okay, so there's a problem here with Ampere's law, and the problem is, what is the magnetic field inside this region here? Let's try to illuminate the problem. So what is the magnetic field inside this region here? Well, Ampere's law tells us, as shown here, that the magnetic field is 0. There is no current flowing across the capacitor plates here. So if I draw a distance r up to some point here and I do the closed loop like this, then I get B is 0 according to Ampere's law. Let's clean that up just a little bit. So if I do a loop, distance r here, and I do the integral B dot dl, then what I ultimately end up with is 0 because there's no current in, let's say, between capacitor plates. Okay, there's no current between the capacitor plates, so the magnetic field must be 0, right? Wrong. Faraday's law, so first off, Ampere and Faraday both knew capacitors posed a problem. So they both knew that this was an issue historically. They just didn't know what to do about it. They didn't know how to fix it. Along comes Maxwell, and he's thinking about Faraday's law, and he says to himself, well, a time-changing magnetic flux gives rise to an electric field. Here's the time-changing magnetic flux, and here's the electric field. So a time-changing magnetic flux gives rise to an electric field. What about the other way around? Time-changing electric flux or a time-changing electric field gives rise to a magnetic field. So what he did was he said, maybe I should be able to take a surface like this, which goes through the capacitor, but has the same circumferential distance here, according to this loop, but it's now a surface. So think of a plastic bag where you've put one end of the capacitor into the plastic bag. And Ampere's law here should give the same answer as the flux of the electric field through this surface here. Whoops, messed my colors up. There we go. So the current coming in here for Ampere's law gives us B equals, mu 0 I over 2 pi r, right? Just helping you remember it by writing it a million times. But over here, what's going on? Well, over here we have an electric flux, okay? There's an electric flux that's non-zero. Now let me just follow the argument in the book because I think it's a nice simple argument. I don't want to go up here and use integrals to do this, okay? The book gives a kind of simple argument here involving the capacitors. I'm just going to follow that. They say that the charge on the capacitor plates is given in terms of the capacitance and the voltage, right? So, and these quantities are, let's actually go ahead and write it with E. We've been using E a lot. So the charge on the capacitor plates, and I usually write positive, sorry, not positive, capital Q, right? So I forgot the book writes lowercase letters as time-changing letters, but I don't really do that. So capital Q here, the charge on the capacitor plates, is equal to the capacitance times the voltage between the two plates. Okay, well, we can rewrite the capacitance as epsilon 0 here, or kappa times epsilon 0, area of the plates divided by the distance between the plates, and we can rewrite the EMF, or the voltage across the plates, as the electric field. Now it's a capital E, it's not a script E anymore, so it's electric field times D, right? So we have epsilon 0 A over D, the capacitance, times electric field times the distance, that's the voltage. All right, so when we do this, we can cancel the D's out, and we're left with epsilon, not script E, epsilon 0 A E is equal to Q. Well, take a look at this quantity right here, E times A. What is E times A? Well, that's an awful lot like the electric flux, isn't it? So we can make a guess and maybe prove later that this has got to be the electric flux right here, E times A. So he comes to this conclusion that Q is equal to epsilon times the electric flux here. And of course, Q determines the current, right? Q is a function of time here. And so since it's a function of time, we can take its derivative to get the current. So Q of T is equal to this. Of course, the flux here is going to change as a function of time. As this capacitor charges up, the electric field between the plates is not constant. It's uniform, but it's not constant with respect to time. So it will increase over time as the charge between the plates increases. I can then form what Maxwell called the displacement current. The displacement current is the quote unquote current flowing between the capacitor plates. Although there is no such thing as displacement current, it's really the electric field that is changing in between the plates. So if we take the derivative here, we see epsilon 0 times the electric flux, times the derivative of the electric flux gives rise to a so-called displacement current. And it is this displacement current which will give us the correct answer for the magnetic field if we now go and use Ampere's law. So Ampere's law says we do B dot dl, and that's equal to mu 0 I. But now what we do, instead of writing I enclosed is 0, we say I enclosed is, well, it's the real current that might be flowing between the capacitor plates. We call it the conduction current, IC, conduction current. That's current that flows inside of a conductor, conduction current. It could even be, well, really so actually, strictly speaking, the conduction current is current that flows in an inductor, plus the displacement current, ID. And that displacement current it's not necessarily a real current. It's really a time-changing electric field. Okay, this is the displacement current. But Maxwell really believed that indeed there was this idea of displacement current. You can see it in his papers that he wrote when he published this, that he really believed that the vacuum was really acting like a dielectric material. In a dielectric material, it is possible to have a current because the charges will rearrange themselves. And so that really is motion of charge. And therefore, displacement current in a dielectric makes sense. But Maxwell tended to be of the belief that displacement current in vacuum was also possible in some way, because a vacuum was treated as a dielectric where the kappa value was equal to 1, right? So a dielectric is described by a kappa value bigger than 1. Well, Maxwell was like, okay, displacement current for a vacuum is like a dielectric, it just has kappa value equal to 1. Now, the conduction current here is 0 between the plates, but the displacement current is not 0. The displacement current is epsilon naught d phi e dt. Okay, and since the electric flux is changing, then we end up getting the same answer there for the magnetic field. Now you can see that, and they don't actually show that in the book. That's why I'm kind of looking puzzled here. But actually, you can show that that is the case, so that we would get the same answer here. So yeah, they don't actually do it here, but it is possible to do it. So let's go ahead and take a look at how that would be done. So what we would do is we would write down, let's see, we would write down the current, give me 1 second here. We would write down the current in terms of the other quantities here. I just kind of want to get this done quickly because we're already over time here. Give me 1 second to find what I'm looking for here. Right, okay. So the time-changing magnetic flux here, I need to clear up a little bit of space here. So let me maybe just scroll up and delete some space for myself here. So if we want to know what the time-changing electric flux is, so we're calculating d phi e dt. This is going to be equal to d by dt of E times A. Now, E is constant on that surface, does not depend on A. So there, and also E is perpendicular to A. If we look at the figure here, we can choose a surface where A is pointing in this direction, and this surface is perfectly flat here, right? So that way there's no angle there between E and A. And then this ultimately becomes A times dE dt. Okay, well, we can get E, I think, from one of these expressions here. Right here, we can get it from right here, actually. So E is going to be equal to Q over epsilon naught A. And then if we take the derivative of this, A d by dt of this thing here, Q over epsilon 0 A, then what we ultimately end up with here is the current in the top. So we have A over epsilon naught. And now we've run into an issue because these are not the same areas here. So this is like area of a disk. Let's back it up a second. Back it up. We'll write it up again real quick. Let's write this as pi r squared. Why am I writing it as pi r squared? Well, if I pick this surface here, then this surface is a disk right here, right? So that's going to have an area of pi r squared. Okay, and then it's d by dt of Q over epsilon 0 A, and this is the area of the capacitor plates, so that's kind of like a length times width type of thing. So pi r squared, and then it's the current up top, and this current is the same as the conduction current IC. But what we're saying here is that this here is the displacement current. This is the conduction current in the wire, not between the parallel plates, right? So there is no current flowing between the parallel plates. Divide by epsilon 0, and then this is the area of the capacitor plates. So now that we've got this, what we can do is, what am I saying actually? The area of the capacitor plates, if we take them to be circular plates, if we take the capacitor plates to be circular like this, well, then they would also have an area of pi r squared as well, right? So, but perhaps there's a little bit of technicality there. We should really maybe make the plates infinite so that the field is completely uniform. Then we could cancel these two things and we'd end up with like ID over epsilon naught here. And so let's complete the picture here. So d phi e, electric flux rate of change, is equal to ID, which is equal to IC, divided by epsilon naught. Okay, and then it says for Ampere's law, we should do integral of B dl, which is equal to epsilon naught, excuse me, mu zero, what is it again? Yeah, mu zero times the displacement current, right? So mu zero times I d, and ID, no, this is not the right expression. Yeah, I want this one right here. Yeah, that's the one I want. So ID is equal to epsilon 0 times d phi m dt, and then d phi m dt, mu 0, epsilon 0. D phi m dt is given as, oh, wait a minute, I'm doing something stupid here. Back up. We don't need to go that far. We already calculated that. We already said it's going to be this, right? So that was what we did up here. So we went through this whole process here to show that the time rate of change of the electric flux would be equal to the conduction current in the wire. So ID is going to be equal to IC. And again, the reason that that is true is because we postulated that if we look at the property of a capacitor, that we could ultimately come down here and take its derivative, and we get that the displacement current is epsilon 0 d phi, the change in electric flux over time. And then we say, okay, time changing electric flux is giving rise to a magnetic field. So we postulate that there must be some sort of displacement current here. And that displacement current now allows us to calculate the magnetic field between the plates of the capacitor, provided that that displacement current is equal to the conduction current. That was the logic there. So this displacement current now is the same as the conduction current. And so now we've reproduced by making this postulate. It really is a guess. It really is a guess. And once we make the guess, we then have to go into the lab and measure that magnetic field ourselves to verify that it is indeed true, right? So we really are guessing here. So, if these arguments don't seem completely clear, number one, maybe I didn't explain it perfectly. Number two, it really is a guess. We're not doing anything like concrete from the mathematics. We're trying to make a guess to fix up the physics. So, so this is ultimately going to lead to B equals mu 0 I over 2 pi r. And this is really going to end up being the conduction current here. Okay, so does anybody have any questions about that before we end things? I believe that is the last topic here. The next thing that the textbook does is they actually write down all 4 of Maxwell's equations. Oh, and by the way, since we found this here, that the displacement current is equal to epsilon 0 d phi e dt, actually it's even better than what I said before. I said kind of like that we were guessing, right? Like we had to guess here to get this. But if you think about it, actually it's a little bit better than a guess, because the conduction current, where are we at here? Scroll all the way down. Okay, here we are. The conduction current here, this term, that term is the current that flows inside this wire right here that is due to an electric field, right? That current, the conduction current, if there wasn't an electric field in the wire, then there wouldn't be a conduction current. No electric field, no current. So as a matter of fact, it's not necessarily that the displacement current is equal to the time rate of change of the electric flux. It's actually that the total current, even the conduction current, must be equal to this epsilon 0 d phi e dt. And I'll let you guys do this. Maybe you can show that that's true by remembering that the electric field is proportional to the current density there. I was trying to remember the name of it. So remember, electric field is proportional to current density, especially inside of a conductor. Inside a dielectric, you might need to make other arguments for that. But I think this actually really makes it clear that the current is directly proportional to the electric field. So it definitely makes sense that Ampere's law should say something about the electric flux and not necessarily the current. So that completes our list of Maxwell's equations. Maybe we can write them down just one time over here before we go. Anybody who really has got to go, feel free to leave the call. Of course, this is being recorded, right? So we can now write down all of Maxwell's equations. The first one that we looked at was Gauss's law. Gauss's law says that the electric flux through a closed surface is always equal to the charge enclosed in that surface divided by epsilon naught. Now, the charge enclosed we could write as some integral over a density, right? Some kind of density here. So we have integrals on both sides if we want to, right? Usually the charge you have to find by doing some sort of integration. Then we have a no-name equation, the integral over a closed surface, again, the closed surface flux, B dot dA, is always equal to 0. This equation implies that there are no magnetic monopoles. Of course, the equation above, Gauss's law, implies the existence of electric monopoles. But this equation implies there are no magnetic monopoles. If this term was not 0, then it would be equal to something that we would call magnetic charge. But since it's 0, we don't have to worry about magnetic charge. Then we have Ampere's law with Maxwell's correction. And I forget, I think the accent goes here. Actually on the first E. So we have Ampere's law. I think last time I wrote it on the second E. Okay, Ampere's law says the closed path integral B dot dl is equal to, and it's mu0 times the current, but the current is epsilon 0 times the rate of change of the electric flux. Okay. And we could maybe be a little bit more careful here. We could say, okay, well, we said, you know, conduction current, yeah, you have a conduction current, that definitely means there's some electric flux there in that wire, but let's go ahead and separate it out. So we'll say we have the conduction current and we have the electric flux piece. So that way, when you have a current, you don't have to worry about going and calculating the electric flux for that current. You can just plug it right into the equation. There's no need to complicate things, right? So this is as simple as we need it to be right here. And then this thing in parentheses, we should put that this is like the enclosed. That's what's enclosed inside the loop that we choose. Or the path, right? Okay. Last one is Faraday's law. And Faraday's law says, in integral form, it says that the integral of E dot dl is equal to minus d phi m dt. Okay, so those are our 4 Maxwell equations. Double check, make sure I didn't make a slip there and write something incorrect. It looks good though. So those are the 4 Maxwell equations. And of course, like I said, when we changed Ampere's law, again, it's a guess, right? We've got to go in the lab and test it. And actually, I think you suspect that it has to be that way because if we were to take let's say like some plates of a parallel plate capacitor and move a magnet between the plates, then we would be giving rise to a current, right? And that current would of course charge up the capacitor plates. Maybe it charges them a little like as we move in, and maybe it charges them a little less as we move away, something like that, right? Then when we charged up the plates, then that has to give rise to an electric field, right? So if we used magnets to generate currents to charge a capacitor, it makes sense then we've created an electric field. So it really does make sense both ways here. Kind of the argument that we gave to develop the electric flux time rate of change piece, we could also do the reverse. We could play with a magnet between the parallel plate capacitor plates and kind of get the same logic that it has to be there, the d phi e dt term. Okay, so what is there left to do? Well, the book just has some stuff on superconductivity, so read that yourself. That pretty much covers everything. There are no examples given here of using all 4 of Maxwell's equations to come to some sort of example problem that we can solve. That's mostly just left to chapter 31 or 32. So let's end it right there, okay? Any questions for me, feel free to stick around and ask. If you don't have anything to ask or talk to me about, you can feel free to leave the call now. I do know I have some emails from a bunch of you that I haven't responded to yet. I will get around to that here in a second.
Professor, I have a quick question from the pre-lecture. Can we go over it right now?
Sure.
Okay. I think it was the key variation problem in the pre-lecture tutorials. It's just that one particular part that has
There's 3 of those.
yes, within that variation problem there's 3, and then I think the second problem, and then there were like a bunch of parts within that problem. Let's
pull it up here.
Yeah, I think
I have to log in again, sorry. Okay, so here, and then
it would be variation problem 29.8.3.
29.8.
29.8, key variation problem 29.8, and then the part would be,
it's like a loop in a magnetic field making an angle.
Mm,
Oh, sorry, I'm on homework part 1. Whoops.
no. It was in the pre-lecture tutorial.
Tutorials, right? Okay, 29.8. Bring it
It
up.
would be the part where it's a square single loop of wire, 4 centimeters on a side with 875 turns.
Okay. Part A or which part?
Part A, I think it was the magnitude of the induced EMF.
Okay, let's go ahead and clean this up. So it lies in the XY plane. So here's an XY plane.
Mm-hmm.
X, Y, Z. It is circular, so I've already messed up.
It's a square actually.
Oh, for me it says, so maybe
Well,
it gives you a random.
I think it was on
29.8?
yeah, but like it says on the thing it says VP 29.8.3. I think it was like part F or something like that.
Oh, part F. Oh, yeah. Oh, it does say square. Yeah.
Yeah. A square single loop of wire 4 centimeters.
So it's 4 centimeters on each side, 875 turns. Okay, so
Yeah.
N is 875. Length is, what was it again? 4 centimeters?
Yeah.
Okay. The loop is in a uniform magnetic field that changes at a steady rate from 0.2 Tesla in the I direction, 1.5 Tesla in the K direction. Okay, so it looks something like this. It starts looking like that, and then it gets bigger in the X direction. It's a little bit bigger in the X direction and negative in the Z direction. So the magnetic field is actually changing from like this value to this value here at a steady rate. So what that means is the rate of change is constant, right? And they give us a delta t here of 3 seconds, so we can figure out that rate of change.
Mhm.
The initial is 0.2, I'll write it as x hat, plus 0.18, put a 0 here or something, z hat. Oh, 1.5, whoops. Okay, and then B final is going to be 0.3 minus 0.2
Z-hat.
z hat. Oh. And then final minus initial gives us delta B.
Mhm.
So 0.10 x hat final minus in yeah, so minus 0.35 z hat, and then this occurs over a steady rate, meaning that delta B over delta T is constant.
Mhm.
So we can divide this now by delta T to get delta B over delta T. So we're dividing by 3 seconds, so it's going to be like 0.03 bar, right? Minus 0.11 6, and then it's going to be a repeating 6, I believe. So this is the delta B over delta T vector, which is what we want here because we're trying to calculate the change in flux, right?
Mhm.
Find the magnitude of the induced EMF in the coil at t equals 2 seconds.
Yeah.
Okay, so in that case, we know that the area vector here is in the z direction, or we can take it to be in the z direction.
Mhm.
So the area vector is in the z direction, and that's just going to be equal to a times z hat. So when we go to calculate b dA, we know what a is. It's constant in the z direction. And we know what b is, and we know what delta b delta t is. So this is the flux, and that's going to be given by, basically we can just do this integral here, and it's going to be b dot a times cosine of the angle between these two. Now, if we leave it as a, that's why I was confused, because I was like, there's something wrong with what I'm doing here. If we leave it as a dot product, we don't have to worry about the angle. The dot product gives us the angle. So if we know the vector b and we know the vector a, we just do their dot product. That's the answer. The area is not changing here, just the magnetic field.
Mhm.
So when we take the derivative, it's just the derivative on b. And the derivative does not act on the dot product itself. So it's just going to be like this, and there's no additional terms here because a is not changing.
Mhm.
Excuse me. To be complete though, if a was changing, then it would end up being like b dot product with dA dt, like this. So we'd have a product rule or Leibniz rule. But this term is 0, so yeah. So dB dt dot product with a. We know what dB dt is. This is equal to dB dt because we were told it was a steady rate of change. Steady rate of change means that the derivative is constant. So delta over delta is the same as the derivative when it's constant. It's like the slope of a line.
Mhm.
So we can just go about computing that now. I mean, now there's no issue here. So the area is 4 centimeters times 4 centimeters, or 0.04 times 0.04 meters squared, which is 0.0016, right? So area equals L squared, which is 0.0016 meters squared. So the, are we looking for the, hold on a second, are we looking for the rate of change of the flux? Oh no, we're
No.
looking for the magnitude of the induced EMF.
Yeah.
Okay. So the EMF is going to be N times d phi m dt. Right? So we have N is 875. We have that the magnetic flux time rate of change is dB dt dot product with A. So the dot product there is just going to single out the Z component, right? So it's going to be 0.0016 times 0.116, like repeating decimal. That's the dot product because the X component is not going to contribute because that's parallel to the loop. And there, we don't have to worry about the cosine because we're actually just taking the dot product. So you multiply these numbers out and you're going to get some answer here. They give about 0.16 volts. There's another significant figure there that they want.
Okay, I just want to make sure. The reason you excuse me, the reason you rule out the 0.03 exat is because it's not within the
So B, or sorry, delta B over delta T. Guess I should just write dB dt, huh? dB dt as a vector is 0.03 bar, comma 0 minus 0.116 bar. And the A vector is, oh, sorry, this is the Z component. The Y component is 0.
yeah.
0, 0, and then A, or L squared. That's the area vector. So dot product means you multiply these terms like this, right?
Mm-hmm.
And then you sum.
Oh yeah, never mind. Yeah. Sorry, I was just a little stuff like that. And then you get okay. And then
Any other questions?
all right, I think I have one more question, which would be the last problem.
On the tutorial?
Yeah, it was the one with the
Magnetic field between a capacitor?
yeah, that one.
Oh yeah, this is like one I gave as kind of like a challenge. Capacitor consists of two parallel circular plates of radius r. The capacitor has capacitance C and is being charged in a simple circular circuit loop. Circuit has an initial current I0 and consists of the capacitor, a battery with voltage V, and a resistor with resistance R as shown. What is the magnetic field in the middle of the capacitor plates at a distance d from the center as a function of time? It's actually a really easy question, but I can see why like it would mess with people. Basically, you have a time-changing current from RC circuits, right? So I0 e to the minus t over RC is your current as a function of time.
Mhm.
Ampere's law says B dot dl equals mu 0 times I enclosed, right? So you can use Ampere's law for like a loop, kind of like exactly what we did in class. Except there's one little thing you have to be careful of here. Since the magnetic field, is kind of building up in magnitude, it's 0 when there's no current. Initially, there's a current I flowing in the circuit, but that I decreases, right? So when the current I begins to decrease, the magnetic field begins to build up, right? And then once it reaches maximum value, that's when you have the maximum change in the value of the current. But eventually what's going to happen is the current is going to taper off, right? As this capacitor becomes fully charged. So once the capacitor becomes fully charged, then the magnetic field has to die down to 0, right?
Mm,
So the question here is, what is the magnetic field in the middle of the capacitor plates at a distance d from the center as a function of time t? Okay, a distance d from the center, so at d between the plates, you have a loop here like this, and the magnetic field is going to be doing something like this, and we're going to go around the loop in some way like this. So the dot product for Ampere's law is positive, and the electric field vectors are kind of coming through like this. And the radius of this loop here we'll call r. Since the radius of this loop let me think about this for a second. So a distance. Oh no. Oh, sorry, I misread the question. A distance d from the what is the magnetic field in the middle of the capacitor plates? Okay, I was overcomplicating the question actually. So I was having to sit there and kind of think about it. Like, okay, what do we do in this case? But no, actually, I just kind of misunderstood the question here. We're looking at the middle here of the plates. So this is the middle. And this is the distance d here. And around this is the magnetic field. Go around in this direction like this. So d is playing the role of the radius here of this loop. So this piece right here, the dl piece, is going to be something like 2 pi d. Now the amount of current enclosed here, we don't actually want to use this term. We want to use epsilon naught d phi e dt. And d phi e dt is going to be, well, this whole term here is going to be given in terms of the current. Well, let's maybe take it a little bit slower. So what is the electric flux going to be? Well, it's going to be the electric field magnitude, right? Times, so d by dt. I forgot my epsilon naught. Let's forget about epsilon naught here for a second. Let's just delete it. So the time rate of change of the magnetic flux is going to be the derivative of the electric field times the area, which is just going to be dE dt times A. And E is going to be given in terms of surface charge density. This is the area of the loop here. This is the area of the loop. And this is going to be given in terms of where do I want to write this? D by dt of Q over A of the plates, which is different. Time epsilon naught in the denominator there, times area of the loop. So the area of the plate is different. So they say that the area of the, the radius of the circular plates is r. So if we want d phi e dt, that's going to be equal to the current I, which is dq dt, divided by the area of the plates, which is pi r squared, times epsilon naught, times the area of the loop, which is pi d squared. And then what we ultimately need is we need integral of b dot dl equals mu 0 times epsilon naught d phi m dt. So now we're ready to get it. So b dot dl, that integral is going to be b times 2 pi d. D is the radius of our loop. So it's 2 pi d here. Mu 0, epsilon 0, d phi m dt is I over pi r squared epsilon naught pi d squared. Cancel, 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 cancel a power of d. What we end up with is b equals mu 0 I d over 2 pi r squared. Is that correct? Yeah, that's correct. And of course, this depends on time. So really it's b of t. The current depends on time. Nothing in the integrals over here in Maxwell's equations involve integrals over time. There are never integrals over time in Maxwell's equations, only ever derivatives with respect to time. So a lot of times the time dependence just sneaks through everything. So b of t is mu 0 I 0 e to the minus t over rc, and then there's a multiplication by d, and then divided by 2 pi r squared. And this thing is a function of d and t. So I should have put b of d comma t. Okay.
Okay. Right. Thank you, Professor.
Does that make sense?
Yeah. Also, right now, my biology class is kind of chasing me right now with an essay, and I'm trying to get it due by tomorrow. Is there any way I can get an extension for part 1 to around Thursday? Yeah.
I would put it to Thursday at 11:59.
Okay.
There we go. All right, there you go. Anything else?
Yeah, that's it. Thank you, Professor.
All right, thank you.
Bye.
Have a good night.